My dear kids, when we apply the push or pull, basically a force on a body, we can change the state of motion. For example, we can change how fast it is moving. We can start to stop the motion like that, right? But the forces can also have one more effect. For example, this body, which cannot translate from one place to other place because it is fixed about this thing, it can only rotate about this place. So forces can also produce a turning effect, and we can call that turning effect as torque. So the torque that we can get from a certain force depends on many things. For example, here we have this thing, right? So I'm going to apply force, basically a push or pull. If I'm applying the push or pull closer to the hinge, you see that the turning effect is reduced, right? But if the same force is applied much further away, same push or pull is applied much further away from the hinge, the turning effect is easier. Are you getting it? So you see that the same force can produce different values of turning effects or the torques, right? Now the torque applied by the force also depends on the angle at which it is acting. Like this, you see, if I apply the force like this, you see that this is the R vector and this is the force which is acting perpendicular. So force is acting perpendicular to the body, push or pull is acting perpendicular to the R vector, we can say, right? So this particular force will have maximum turning effect. My dear kids, if the same force is acting along the position vector, you see that this is the position vector, right? And this is the force I'm applying, right? Let's say that I'm pushing the body, right? Like this. So this force does not have any turning effect. Same force, but no turning effect. I believe you are getting the idea. So the torque of a force has, many applications across the rotational motion, and it performs the same duties as the forces in the linear motion, right? So let us learn more about the torque and the related concepts in this particular lecture and cover them one by one in a crystal clear fashion. Let's do that. Alright, so hello, welcome on this beautiful platform of Physics Wala. This is your physics mentor Gaurav Tiwari. My dear kids, today we are going to learn the concepts of a beautiful chapter called Rotational Motion. My dear kids, many kids are afraid of this chapter because they believe that this chapter is long. Yes, it is long because in the kinematics of linear motion, you studied kinematics and dynamics in separate chapters. But right now, about the rotational motion, when you're going to study, the kinematics of rotational motion and the dynamics of rotational motion both will be covered in one single chapter, which is why the chapter gets bigger. My dear kids, we will cover each and every concept of this chapter in an extremely detailed manner with a lot of interesting and important numerical problems. My dear kids, by the end of the class, every concept of this long chapter will be crystal clear to you, and at the end of the class I will also share a DPP which is going to be free for you. You can access that DPP through the link given in the description and practice it directly on the PW app. My dear kids, PW is innovating the way we learn, and this channel is just another honest attempt in the same line of action. Now without any further delay, let's start covering this chapter. Alright, so if you just move ahead on the NTA website and download the syllabus and look for the syllabus of this particular chapter, you will find that these are the topics that are mentioned under the topic of rotational motion. The lines which is not highlighted, we have already covered in the previous one shot of center of mass, right? And the lines which are highlighted or the underlined, so we will be covering those points today, right? So all those points we have written in the bullet points like this. So we are going to cover each one of them one by one, right? Now, it is always a good idea to categorize what we are going to learn into available categories, so we can easily cover them one by one, right? Otherwise, we look at all these terms, the chapter looks very, very long, right? So you see that there are three categories in which we can divide all the topics, right? All the topics can be divided into three categories. First, we're going to talk about some terms, right? First, we're going to talk about some terms, right? Terms of rotational motion. This is the first category, right? We are going to deal with the basic terms of rotational motion. I'll show you, right? Then after we will discuss the kinematics of rotational motion, and then we will talk about the dynamics of rotational motion, right? And then finally we will deal with the moment of inertia and all those things as well. So those are also a part of dynamics only, but we will be discussing in this format, right? So let us discuss with the terms of rotational motion first, right? There are some basic terms that we need to discuss, right? So over here we have it, okay? So right now you see that it is very important for us because we are going to talk about the rotational motion of rigid bodies, right? So we need to first understand what is a rigid body in physics, right? So let's look at that. So here you see that when the person is performing these calisthenic exercises on this pole, right? So clearly there are a lot of stresses or forces that are being applied on this pole, right? And at the same thing, at the same time, you see that here on the same pole, a lot of forces are being applied by this athlete as well, right? So you see that there is a basic difference between these two, right? Here the pole does not deform, here the pole gets deformed, right? So the nature of the bodies is such, we can classify them into two separate categories, right? We will call one category is rigid body. Rigid body is a body in which when you are subject that body to multiple forces, right? What happens? The body performs motion, but the shape of the body does not change. That means if you take any two random points, the distance between these 2 points does not change, right? So whatever discussion we are going to do about the rotational motion, we will keep that in mind, that we are discussing with the rotational motion of the rigid bodies. So if forces are applied, the body will not, compress or expand. So the distance between the 2 points of the body will not change, right? Okay. So here you see that clearly this pole is not rigid, because when you apply the force on the pole, so right now these two ends are at this distance apart, and when this is bent, you see that these 2 points are now much closer, right? So yeah, so this is the idea behind it. So we are going to just discuss the moment of inertia and all those things, lot of terms about the rotational motion, but the rotational motion of rigid bodies we are going to talk about, right? So that's the idea, right? So what is a rigid body? It is defined as anything on which the distance between 2 points never changes whenever you apply the forces and all, right? So non-rigid body, as I said, the opposite of that. So clearly if you apply the forces, the distance between the 2 points of the body may change. That's a non-rigid body, right? Now, how many types of motions are there? Right, we are going to discuss the rotational motion, but in general, what kind of motions are possible basically? So here you have the first possibility of translatory motion. So we will discuss more about that. Then we have rotational motion, and then finally we have combination of these two motion. Let us first discuss all three of them one by one. So let us first discuss the translational motion, right? So here you have translation motion. So just from the definition perspective, when will you say that the body is performing translatory motion? So let's have a look at that. So here you see that there are 2 points on the body and the body is moving like that. What will happen? We can say all these 2 points have the same displacement distance, right? And the same velocity, same acceleration, everything is same for both of these points, right? So the translatory motion, these linear terms are same for each and every point of the body, right? And if you look at the trajectory, you see that the path of every point is parallel to each other, right? You look at this point and this point. Look at the path of this point. Let's say you take the body from here to here, and now you trace the path of any random point on the body. It traces the path like this, right? And another random point traces the path like this. When the body is shifted, these are the paths of these two random points A and B, right? You see that the paths are parallel to each other. They need not to be exact parallel straight line. You see that if you take the body and you move it like this, so it was initially here and finally it is here. So the path of A will move with the body like this and path of B moves like this. But you see that during the entire journey, the path remains parallel to each other, right? So in the translatory motion, what happens? When the body performs a translatory motion, every particle follows a path which is parallel to each other, right? If this path is a straight line, then the motion of the body is the rectilinear motion, right? And if the path followed by the particles of the body is not a straight line, then it is a curvilinear motion, right? So this is curvilinear translatory motion, this is rectilinear translational motion. So we can say that, right? So I believe the idea is very, very clear. So in the translatory motion, what will happen? This is the body, right? So what is happening when the body is shifting from one point to other point? We can talk about any two random points, right? What will happen? The path of those 2 points will remain parallel. So it can move like this as well, and it can also move like this. So that does not changes a lot of things. So yeah, so we have translatory motion. We have discussed everything about the translatory motion in the previous one shots. We have talked about kinematics of 1D and 2D, right? So all of that was translatory motion and different categories of translatory motion, right? And we have already discussed dynamics of translatory motion, like Newton's laws of motion, work power energy, all of that is discussed, right? Now we can talk about the second part, which is a rotational motion, right? Just recall, we have understood in the translatory motion, when the body performs a translatory motion from one place to other place, every point covers the same distance, same displacement, same velocity, same acceleration. For the variables are same for all these points. The linear variables are same for all the points. But when the body is under rotational motion about some point, you see that it is under rotational motion about this point, right? Like this. So now you think about it. Look at the point A, it follows this path, and look at the point B, it follows a much larger path. Do they have the same path length or the distance? We can say no. Do they have the same linear parameters? Are they covering same with the same linear velocity? Do they have the same linear velocity? We can say no. Think about it. The point A is inscribing this little circle and point B is moving on a much larger circle, right? So when this, when this thing is going to rotate and will complete one full circle, so point A will complete a smaller distance in the same time, while point B will cover much larger distance in the same time. So point B has a clearly higher velocity. You see that? So when a body is performing rotational motion, all the points of the body do not have the same distance displacement, right? All the points of the body do not have the same distance displacement, velocity, acceleration, all those things, right? That can be different, right? So distance, displacement and velocity of these points can be different in the rotational motion. However, it was same in the linear motion, right? So right now, if you say that which quantity remains same when they move, so that is angular properties, right? Angular properties. What are the angular properties? Like angular velocity, like angular angular displacement, like angular acceleration. Those properties are same for all these points. For example, when the body is moving from here to here, this body is performing 90 degrees angular displacement or pi by 2 radian angular displacement. So for each point the angular displacement is only pi by 2, right? And let's say this point is moving pi by 2, this pi by 2 displacement is covered in 1 second. So the velocity of point A, angular velocity of point A is pi by 2 radian per second. For point B also pi by 2 radian per second, right? Because both the points are covering pi by 2 radian simultaneously in the same 1 second, right? So these points have the same angular velocity. So we can sum it up. When the body is performing rotational motion, these 2 points do not have the same linear velocity because point A is covering different distance and displacement in the same time as compared to point B. So different values of distance displacement, that means different speeds and velocities for the given time. But what will happen is if you talk about the angular speeds, so angular speeds are definitely the same, right? Now let's talk about the next part, right? So so we have talked about this part already. So yeah, so they have the same angular parameters. So when the body is performing translatory motion, so what happens in that case, my dear kids? When the body is performing translatory motion, its linear parameters remain same. When the body is performing translatory motion, its linear parameters remain same. What are the linear parameters? Distance, displacement, velocity and all those things, right? Linear velocity and all those things. But when the particle is performing rotational motion, its angular parameters remain same, right? Linear parameters of different points will be different, right? Okay, so I hope the idea is very, very clear about this one. Now let's move on and talk about the next idea. All right. So what is rotational motion? Just to define it, if a body is performing rotational motion, that in that case, every point on the body will inscribe a circle, right? So yeah, you see that? Point A and point B, you can take any random point, it is inscribing a circle. So when that happens, we can say the body is performing rotational motion. When the fan is moving, so fan is performing rotational motion about the axis about which it is moving, right? The fan is under rotational motion, but you can take any point on the blade of the fan, right? You see, this is the fan, it is moving about this point. Let's say these are the blades of the fan, let's say these are the 4 blade fan. Let's say this point is inscribing a circular motion, right? Okay, this point is inscribing a circular motion in a different radius, right? But the fan itself is rotating about this particular axis. I believe the idea is very, very clear, right? So this is written, a rigid body is said to undergo pure rotation if it moves in such way that the constituent particles are moving along the circular arcs, right? So this particle is moving along the circular arc, this particle is moving along the circular arc, right? Now motion of rigid body, the next thing is examples of rotational motion. So here is the first thing, right? The motion of a hinged door, I have already created a short for you, right, where I have shown you in the beginning of the video itself, you may have seen, I have explained some ideas with the doors, right? So if you look at the door, right, what happens? This door is fixed about this axis. You cannot take that door and move it right? So the door is definitely not under translatory motion. When you push or pull the handle, instead of moving the door from this room to another room, right, what really happens is it moves about this hinge, right? So this is the rotational motion about this hinge, right? Look at this thing, motion of a ceiling fan. The ceiling fan is clearly performing the rotational motion, right? Now, general planar motion. So general plane, we should call it general plane motion. So general plane motion is generally a combination of these two, right? For example, when a body is rolling, it's a very, a classic example of a general planar motion. So what really happens is, when the body is rolling, it moves from one point to other point as well. So here, this is the body. When it is moving, let's say a wheel is moving and moving ahead like this. When the wheel is moving and proceeding forward, so what is really happening? You can combine two different motions to get the rolling motion, right? First is, it is translating from one point to the other point, and second, it is also rotating about its axis, like the wheel is moving about its axis, right? So this is the combination of these two, you call it rolling motion. I believe the idea is very, very clear. All right, so let's move on and talk about the next one, right? Planar motion. So this is the planar motion. So now you see that these were the basic terms of the rotational motion that might create hindrance if we had missed them. So that was a little bit of patience that we need before we enter into the details of a chapter, right? So basics of the chapter is that much only. Now we can move into the serious part of the chapter, which is kinematics of the rotational motion, after which we will talk about the dynamics of rotational motion. So what do you mean by kinematics of rotational motion, my dear kids? When we talk about the kinematics of rotational motion, so we understand that rotational motion, in the rotational motion, any change can happen due to torque, right? Torque is the rotating effect of, turning effect of a force. So what really happens, right? In the case of rotational motion, what really happens when you apply the force like this such that it produces a turning effect? Now, you see that. So, what really is happening in this case? Let's say that here we have this body and it is going to move about this axis, right? So, which is passing through the diameter. Let's say that I apply some torque, right? And it is going to rotate like this. Now, you see that if I apply the force over here, it is not going to do anything, right? I can simply move it. I can push or pull it along the axis with the help of force. But if I want to rotate it, I have to apply force somewhere else. And when I push it, let's say from here at this point, let's say like this, so it starts rotating. Now, if I want to increase the rotational speed, in that case, I have to keep applying the torque like this, right? Yes or no? So if I want to stop the rotating body, again, I am applying a torque, right? So in the case of rotating body, to start the rotation, you need torque. To stop the rotation, you need torque. To change the angular velocity, you need torque, right? And understand that the force was performing some duties in the case of linear motion. Exact same things are applied for the torque in the rotational motion, right? So force was changing the state of motion when the body was under translational motion. Torque is going to create the same changes when the body is under rotational motion. I believe the idea is very, very clear, right? So here, when we talk about the kinematics of rotational motion, we are discussing the terms of motion, which is how fast the body is moving. We will talk about initial velocity, omega, initial angular velocity, right? Omega naught, you can say. Then final angular velocity, omega, right? And then we will also discuss angular acceleration. We will also discuss, let's say, the time is same, angular displacement, right? Now, it might remind you of something, right? In the beginning, we were discussing something about the kinematics of motion, the motion in 1D, right? We were discussing about few things. What was that? Right, we were discussing about linear displacement, linear velocity, linear acceleration, all that, right? So when we were discussing the terms of motion without talking about the cause, if the angular velocity is changing, there must be some torque. A particular value of torque will bring in a certain value of change in the angular velocity. But we are not interested in talking about how much torque is involved in all those interactions. So basically, any change requires torque, which is the cause, all right, cause, right. So we are discussing rotational motion without talking about the cause. This is the kinematics of rotational motion, right. What will you expect in the kinematic analysis of rotational motion? Very important part. So here you can say that we can talk about, let's say, in the previous kinematic analysis of rectilinear motion, we had certain criteria. For example, if the translatory motion had a uniform acceleration a, right. So yeah, here you will have angular acceleration, there was a linear acceleration, right. So what will happen, due to that uniform acceleration, the velocity will change from u to v, right. So initial velocity here is u, and here it is omega naught, angular initial velocity, and similarly the final linear velocity was v and final angular velocity is omega, right. So what will happen, the particle was covering the displacement which was s, right, and here the displacement is angular displacement, right. So in the previous scenario you had equation of motion, v is equals to u plus at, right. Final linear velocity is initial linear velocity plus linear acceleration times into time, right. Now if you want to write down the same equation in angular terms, you will write it in the same way. You will say that the final angular velocity, instead of final linear velocity you have final angular velocity, initial linear velocity you have initial angular velocity, plus acceleration, so you have angular acceleration into time. Now it can tell you that this equation is only valid when the linear acceleration was constant. Similarly, this equation is only valid when the angular acceleration alpha is constant. You call such equations as equations of uniformly accelerated linear motion. So you will call these equations as equations of uniformly accelerated angular motion. I believe it is making sense, right? So now if you want to analyze the angular motion or the rotation of a particle, something is happening. Its angular velocity is changing, it is going to cover some angular displacement in some time, right. So in all those changes, what are we basically discussing? We are discussing about these equations, right. So you can talk about the other variations as well. So v is equals to u plus at, the second equation is also there, displacement is ut plus half linear acceleration into time square, right. So you can derive the other format of this thing. So for example, displacement is this, angular displacement will be, there was linear displacement, here you have angular displacement, omega into time plus half, in place of a you have alpha into t square. I believe it is making a lot of sense, right. Now let's move on and talk about the next idea. You have one more equation, we can do that as well. V square is u square plus 2as, and here you will be omega square is omega naught square plus 2 alpha theta, all right. So these are the same variations of the linear equations of uniformly accelerated rotational motion, right. So these are the ideas, right. We are going to apply those ideas, right. One change you will observe when we are going to discuss the angular motion, right. For that I have written a lot of things, right, and I will explain you as it comes, right. So let's move ahead and solve some problems as we see them. So first of all, we will have a look at angular velocity. So as you know that linear velocity is how fast the particle is covering the linear displacement, right. So the particle is covering displacement s, right, in the time t, and it is not accelerating, so you will call it displacement over time is the linear velocity, right. Similarly, if the particle is moving and it is not accelerating, it is rotating only with a certain velocity, let's say it is moving at 1200 rpm. So if in the question they are giving you the particle is moving, object is moving at 1200 rpm, right. So this line should sound in your brain exactly the same as a body is moving with 20 meter per second, right. So you will call that a body is moving with 20 meter per second, it is uniformly, it is moving with no acceleration. Similarly, if a body is moving at 1200 rpm, means there is no acceleration, it is like a fan moving at 1200 rpm without accelerating, right. So if there is a constant angular velocity, so you will call it angular velocity will be the angular displacement covered over a certain time, right. So angular displacement theta covered over a time, right. Now there are various ways to write down the angular displacement, right. If a particle is moving one full rotation like this is the body, it moves one full rotation, you can call it 360 degrees, or you can call it 2 pi radians, right? Generally, we represent the angular displacement in radians. It's a SI unit. So that's it. So you see that for angular displacement, we use radians mostly, right? But not always. Sometimes they will tell us the units will be RPM or RPS. So rotation per minute or rotation per second. So you see that if you know there are, let's say, n RPMs, right? Okay. That means, let's say, 1200 RPMs. A body is moving at 1200 RPM. Okay. So how will you write down in the radian per second, right? Because you are interested in writing radian per second. That is the correct way of writing the SI unit of angular velocity, right? So how will you do that? How will you make the change of units in that case? So very easy, you can do that, right? So 1200 RPM, one rotation means 2 pi radians, right? So 1200 rotations means 1200, first of all, 2 pi. So now what you have done, you have converted rotations to radian, right? So now you can write radians, that is per minute. PM, RPM is rotations per minute. You have multiplied by 2 pi and converted rotations into radian. Now per minute part you can deal with. We want per second. So for a minute is this much. So for a second you have to divide by 60. So it is radian per second. You see that RPM is converted to radian per second when multiplied by 2 pi by 60. Very simple, right? So yeah, this is the idea. If RPM you want to convert into radian per second, the SI format, you can multiply with 2 pi by 60. Remember, if in the numerical they are giving you MCQ type question, and in NEET they will give you MCQ type question only. So they are not giving you, let's say, the units in radian per second. So you will not force it, because the options are giving in RPM and rotations per second and all those things, right? So you will not force, convert and all, do all those things, right? Yes or no? So if they are asking you the velocity in RPMs only, why will you convert? So always look at the options before converting, because you will find that there are multiple types of numerical which is asked in the previous year. So I'll show you better numericals than the previous year numericals, right, in this class itself. Let's have a look at that. Now, angular velocity we have talked about. So angular velocity has a dimension of t minus. Why? Because this theta is dimensionless. So no dimension upon t, so it is t minus. This is the dimension of angular velocity. Angular velocity is an axial vector. So if the particle is moving like this, right? If this is a rod, it is moving about this axis like this. So if you will not call the angular velocity direction is clockwise or anti-clockwise. This is the sense of motion, right? So if you observe it from here, it seems clockwise and all that, right? But it is an axial vector. The direction of omega is, you can curl in your fingers in the direction of rotation, and you can tell that it is pointing outwards. That's the axial vector you call it. You can also call it pseudo vectors and all, right? So if a body makes n rotations in t second, then this is how you can figure out, right, angular velocity in radian per second. So but as I have already told you that part, right? So angular velocity of a particle A with respect to other moving particle B is the rate at which position vector of A with respect to B rotates at that instant. So that part I will explain while solving the numerical problems, because to explain this with that, it sounds complicated, but it is not. Sometimes in the NEET exam they can ask you a good quality numerical, then the point 4 is going to help you, right? So to explain point 4 in a much better way, I'll be using the position vectors and I'll explain you the concept in a much clearer way. You have to wait till the concept of torque comes up, right? So yeah. So the average angular velocity is displacement, net displacement for a time interval. So yeah, this is it. And instantaneous angular velocity is quite useful. So sometimes they define the displacement d theta for a time dt. So d theta by dt is omega. Sometimes they give you in the numerical the angular displacement covered by a particle is variable, right? So it does not always cover the same angular displacement. Like the clock, in a clock you can say the seconds hand always covers the same angular displacement in 1 second, right? The minutes hand also cover the same angular displacement for every minute, right? But let's say that there is a weird kind of clock, so that does this thing in 1 second. In 1 second, one of the weird hand goes like this, and the next second it covers more displacement. In next second it covers more displacement. So clearly The displacement is not a constant, so displacement is here the function of time. So if that happens, you can differentiate such displacement and get the value of angular velocity. For example, displacement is changing with time as 2t square plus 3, right? So what will be the angular velocity after 3 seconds? So what will you do? You will differentiate it and you will get d theta by dt. So once you do that, differentiating will give you 4t, right? And differentiation of 3 is going to be 0. We have to find angular velocity, let us say at t is equals to 3 seconds. So what will happen? So omega at t is equals to 3 seconds, put t is equals to 3 in this one. So 4 into 3, that is 12. Let us say it is radians. This is given in radians, right? So it is going to be radians per second. So this is how you can solve simple kind of problems. Don't need to be, puzzled by looking at this t square and all in theta. No, don't do that. You just differentiate theta as you were differentiating linear velocity, linear displacement, right? You were differentiating linear displacement with the time, you got the linear velocity. Similarly, differentiating angular displacement will give you the angular velocity, right? And the series is same. Differentiating angular displacement with time, d theta by dt, gives you angular velocity. Differentiating angular velocity with the time will give you angular acceleration. Same, right? Just in the previous case, in the linear cases, you differentiate linear displacement with time, you get linear velocity. And then when you differentiate linear velocity with time, you get linear acceleration. Same things are applied over here. So simple kind of numericals can be solved right away like that. So now let's move on and talk about the first numerical over here, right? So now we can solve simple kind of numericals. Let's look at this one, very simple numerical. Let's have a look. First of all, the angular velocity of a wheel increases from 100 radian per second to 300 radian per second in 10 seconds, right? So it is 100 radian per second to 300 radian per second in how much time? 3 seconds. Oh, sorry, 10 seconds. All right. So the angle rotated by the wheel in this changes. You know that if the initial velocity is changing to some value of the final velocity over a time interval, the particle will cover some displacement, right? So let's say that if the particle had initial velocity of 20, it has some acceleration due to which it acquires a velocity of 40. So while the change happens, the particle will proceed and it will cover some linear displacement. Similarly, it is rotating, right? So when it is rotating at 100 radians per second, and then finally it starts rotating at 300 radians per second over the 10-second interval, so it would have covered some angular displacement, right? Let us say that that angular displacement total comes out to be theta, okay? The angle rotated in radians we have to talk about. So that radians we have to tell simply, right? We don't have to tell the number of rotations. We have to tell the angular displacement theta in radian directly, right? If we had to tell the number of rotations, in that case, we would have divided theta by 2 pi. Yes or no? Let's say that you got 4 pi radian and all those things, right? So you just divide whatever radians you are getting by 2 pi, that will give you the number of rotations, right? So here it is. Initial angular velocity is this, final angular velocity is this is the time, right? So first of all, you can easily calculate what will be the acceleration in this case. Very simply, you can do that. So v is equals to u plus at, or a is equals to v minus u upon time. This is it. So as you can also remember, this is the first equation I have applied. V is equals to u plus at, or omega is equals to omega naught plus alpha t. So alpha is equals to going to be omega, final velocity is 300, initial is 100, time is 10 seconds. So change in velocity over time simply 200 by 10 is 20 radian per second square. All right, so this is the angular acceleration, right? Now you can look at the problem very simply. A particle which is rotating with constant acceleration, right? How much displacement will it cover in 10 seconds? Very simple, right? So S is ut plus half at square, you can apply, right? And yeah, S is ut, so u is 100 into t plus half at square. So half a is 20 into t square, so 10. So in 10 square, you can write down 20 over here itself. So why write another line? It is very simple. So 10 square is going to be 20. So this is going to be 10. All right. So you have 1000 adding up with another 1000. So you have 2000. So 2000 radians is the correct answer. So option D is the correct answer over here. So I believe the idea is very, very clear. Yeah, so option D is the correct answer. Now let us move on and talk about the next one. So a rigid body rotates about a fixed axis with the variable angular velocity equals to alpha minus beta t at time t, where alpha and beta are constant. So don't need to worry about this kind of problems, right? First of all, they are giving you velocity which is changing, angular velocity which is changing. So, as I have told you, angular velocity is alpha minus beta t over here. No need to worry about that, right? How will you find acceleration? Differentiate it, right? You know that differentiating linear velocity gives you linear acceleration. Differentiating angular velocity will give you angular acceleration. So differentiate that, right? So this is the angular velocity at time t, alpha and beta are constant. The angle through which it will rotate before it comes to rest. We have to find the angle that is it's going to rotate before it comes to rest. That means theta, such that the final velocity becomes 0. Making sense? Very easy. Right. So clearly, first of all, differentiate this d omega by dt, right? Differentiating that, alpha and beta are constant. So differentiating a constant gives you a 0, and differentiating this thing will give you minus beta only, right? Okay. This is the acceleration. This is the angular acceleration. Yes or no? Alpha, right? One way of learning that could have been omega is equals to, v is equals to u plus at. You think about it. Omega is equals to omega naught plus alpha into t. So instead of acceleration, you have this thing, right? So minus beta is the acceleration. So yeah, so once you have the acceleration, now the problem is again this: a particle is accelerating with minus beta radian per second square, right? After how much angular displacement it will stop? They are not talking about the time, right? So there is equation that talks about the displacement without talking about the time. That is the third equation of motion, right? So omega v square is u square plus 2as. So omega square is omega naught square plus 2 alpha. In place of s, this which is the angular linear displacement, you have theta, which is angular displacement. So now you can easily apply all the available things. So final angular velocity you want to be 0, because the body eventually comes at rest, right? And initial angular velocity, what will be the initial angular velocity at t equals to 0? So you see that when you put t is equals to 0 over here, the initial angular velocity will come out to be alpha minus beta into 0, which is alpha only. So I can write down, instead of omega naught square, initial velocity will be alpha only, right? Again, for those who could not understand, initial velocity means velocity at time equals to 0. So when you put time equals to 0 in this one, so beta into 0 will become 0. So initial velocity is only alpha. So that's why I'm putting initial velocity as alpha. Now, acceleration is minus beta. Here we have find out, and theta. So you just take this thing over this side, minus sign will come up and minus sign will be cancelled out. So minus alpha square is minus 2 beta into theta. This and this cancels out. So theta is going to be alpha square upon 2 beta. Theta is going to be alpha square upon 2 beta. I believe it is making some sense. All right. Theta is alpha square upon 2 beta. I believe there is no problem in that particular part. Right. So alpha square upon 2 beta, A is the answer. Let's move on and talk about the next one. Now look at this one. Right. Now look at this one. So what is happening? A wheel is subjected to uniform angular acceleration. So what is happening? A wheel is subjected to uniform angular acceleration about its axis, right? A wheel is subjected to uniform angular acceleration about its axis, right? Equations of motion will work, right? Initially, its angular velocity is 0. Data, omega naught is 0. In the first 2 seconds, it rotates through an angle theta 1, okay? In the first 2 seconds, it covers an angle theta 1. Very easy. In the next 2 seconds, it rotates an angle theta 2. We have to talk about theta 2 upon theta 1. So this is the situation. This is the rod, let's say, over here. Initially, it was here. In the first 2 seconds, it is going to come up over here, let's say. This is the first 2 seconds, right? Or let's do this thing, right? In the first 2 seconds, the rod is over here. So at t is equals to 2, the rod is here, right? And after another 2 seconds, the rod comes up here. So this is again after 2 seconds, 2 more seconds, that is at t equals to 4, right? So in the first 2 seconds, it completes an angle theta 1. So this is theta 1. And in the next 2 seconds, it rotates through angle theta 2. So this angle is theta 2, right? Now you have to talk about theta 2 upon theta 1. That's it, right? Okay. Now understand that when we talk about the equations of motion, like v is equals to u plus at, right? S is ut plus half at square. So those equations are defined for total time t. For example, when you say that s equals to ut plus half at square, all right? So it tells you that from the beginning, when the initial velocity u was taken, from that point, how much time is passed, let us say after 5 seconds, how much displacement will be covered. So it will tell you the displacement from the beginning, right? Okay. So when you apply the same variation of this thing, so instead of linear displacement, you have angular displacement, right? Instead of s is ut plus half at square. So this is omega is omega naught t plus half alpha t square, right? So you see that this equation is telling you, not omega, s means theta. Angular displacement is theta. So here it is, when you are getting theta, the angular displacement for the total time interval. Understand that. If you put t is equals to 2, it will give you this much angular displacement, fine. Theta 1 you can get in the 2 seconds. But when you put t is equals to 4, it is not telling you only this much. It is telling you from the beginning to this much, right? When you put t is equals to 4 seconds, it is going to tell you total. So let's call the total displacement is theta 3, which is covered in 4 seconds. And if you subtract from theta 3, if you subtract the theta 1, the remaining value is theta 2 only, which is something we want to find out, right? This is the common sense we want to develop while practicing, right? So when the formulas are applied, remember that the values like displacement, we are calculating for the total time, right? So you can write it somewhere. So in the equations of motion, of uniformly accelerated body, parameters are defined. Parameters are defined for the total time interval. Remember that. Many kids do the mistake, and we don't want that, right? Parameters are defined for the total time interval. The initial velocity was this, final velocity became that much. So that change of velocity happened over the entire time interval, right? Okay. So let's talk about that. So here we have it. Theta 1 will be the displacement particle has covered in the first 2 seconds. So it is started from rest, right? Initial velocity was 0. So this portion is 0 anyway. So 0 plus half, acceleration is alpha, and this is 2 square. And then theta 3, this is the displacement covered in the 4 seconds. This is half alpha 4 square, all right? So theta 1 is clearly 2 alpha, and theta 2 is 4 square is 16, and 16 by 2 is 8. So it is 8 alpha, and clearly theta 2 is theta 3 minus theta 1. So theta 2 is going to be this minus this, which is 8 alpha minus 2 alpha, which is 6 alpha, right? Now we want to find out theta 2 upon theta 1. So theta 2 upon theta 1 is clearly 6 alpha divided by 2 alpha, which is 3. I believe the idea is very, very clear. So option C is the correct option, right? I think there is no confusion in this part. Now let's move on and talk about the next one, right? Now look at this one. What is really happening? Look at this question. An electric fan has blades of length 30 centimeter, right? An electric fan has blades of length 30 centimeter as measured from the axis of rotation. Good. If the fan is rotating at 1200 rpm, the acceleration of a point of the tip of the blade is about. Acceleration of the point of the tip of the blade is about. So what will be the acceleration of the tip of the blade? So this is simply we have to tell, right? So no need to worry about that. So just some misconceptions we have to deal in this kind of problems, right? So let us discuss that so that you can solve these problems also very, very easily, right? Okay. First of all, let's read that problem so that you can get some idea about it. Here the body is rotating, but it is not accelerating. So why are they talking about the acceleration of anything? It is rotating at 1200 rpm. The fan is rotating at 1200 rpm. So why are we even talking about acceleration? Understand that when the particle is moving on a rotational manner, when there is a rotational motion going on, we just don't have angular acceleration. We have more than one things going on at the same time. So what are those things? Let us discuss that. Let us discuss the terminology so that we can solve such problems. Here you can see if one option was 0, some kids might have clicked 0 because the body is rotating at 1200 rpm, right? And in case if they were asking what is the angular acceleration of the body, it is rotating at 1200 rpm. What is the angular acceleration? There is no change in the angular velocity. It is always 1200 rpm. There is no change in the angular velocity. So there is no angular acceleration. But right now, they are not talking about the angular acceleration of the fan. They are talking about a certain point. Let's say that this is the wing of a fan, right? And the span of this thing is 30 centimeter. The length of the fan is 30 centimeter, right? So this is the point at the tip of the blade, right? You see that clearly the tip of the blade is going to inscribe a circular motion because we have seen it in the case of rotational motion. Every point on the body performs the circular motion. So you look at that, this path, this is moving on a circular path like this is moving on a circular path which is much smaller, like that. I hope it is making some sense to you, right? So you see that for the entire body there is no angular acceleration. But when you talk about every particle of the body on the rotational motion, this particle is capable of having two accelerations, right? What are those two accelerations? First is acceleration along the path like this. Second is, since it is on a circular path, there is always a centripetal acceleration, right? When will certain acceleration act? Understand that for this particle, the net acceleration will be resultant of these two vectors. This is tangential acceleration. This is the centripetal acceleration. Understand that. When the particle is only rotating with a certain, let's say that velocity, there is no angular acceleration. So there is no angular acceleration, the body is not getting faster or slower. So you see that this particle is not going to accelerate in this direction. It will continuously move with the same angular velocity, right? So in that case, if alpha is 0, that means there is no component of acceleration along the tangent. At is 0. Got it? If alpha is 0, if angular acceleration is 0, there is no tangential component of the acceleration. Remember that. And anyway, in any way, what is happening? This particle is on the circular path. So centripetal acceleration is always there, right? So even if there is no angular acceleration, there is one acceleration due to the circular path, which is the centripetal acceleration. So only centripetal acceleration will be there. Okay. So remember that if I talk about the angular acceleration of the fan or the blade of the fan, it is 0. It is rotating at 1200 rpm. The velocity is not changing. But if I talk about any random point on the body, so every point on the body performing rotational motion, every point on the body performs a circular motion, right? The point on that body performs circular motion, right? So these points can have their own parameters. So for example, this point has two accelerations because the body on the circular path has two acceleration, tangential and radial, or the centripetal acceleration. Centripetal acceleration is never 0 if it is circular motion, right? So it is never 0, and tangential acceleration will be 0 if it is not accelerating. Clear? I believe there is no problem in this part. And centripetal acceleration, you know that if a particle is there, so r omega square or omega square r, whatever the way you want to remember it. So centripetal acceleration of a particle that is moving at a distance r away from the center at an angular velocity omega is r omega square, right? So that particle which is at the edge of the blade, it is going to be at 30 centimeters away. So r for that is 30 centimeter. All the options are in meters. So clearly I don't want to put r in centimeters only. So r is in now in meters by dividing by 100. And omega square, omega is 1200 rpm. They're not using rpm rotations as the measurement of distance and all. We have to talk about we have to convert that rpm into something that we can understand, right? So rpm will be converted into radians. So 1200 into 2 pi is number of rotations per minute, and 60 divided by 60 there is number of rotations per second. So now we have converted into seconds also, right? So clearly you can just solve it out and now you will get the answer, right? Just solve it out and you will get the answer. I hope there is no confusion in that particular part. And yeah, that's pretty much everything about this numerical, right? So the same things I have written over here. So in which case you will not have angular acceleration and all. The same things that I have explained, I have written over here. So if angular velocity is constant, angular acceleration is 0. If angular acceleration is 0, that means there is no tangential acceleration of the points on the body performing the rotational motion. There is only centripetal acceleration alpha r square. I hope it is very, very clear, right? So yeah. So you solve it and you'll get this much, right? So 1200 by 60 into 2 pi. So that is, this is one part which is written. Okay, and this 0.3 is coming up because 30 divided by 100. So that's it, 0.3 is coming up. Now let's look at the next one. Now let's look at the next one. Consider two satellites S1, S2 with the time period of revolution 1 hour, right? So there are two satellites S1 and S2 with the period of revolution is 1 hour respectively, revolving around a planet in the circular orbits, right? They are revolving around the planet in the circular orbit. So they are not, in the question it is misprint. So in the first satellite, it is revolving around a planet in a certain time. So time period for the first satellite is 1 hour. Time period for the second satellite is 8 hours. Right? This is not written. So now you can read it. Consider two satellites S1 S2 with the periods of revolution 1 hour and 8 hour, right? Respectively. Now it makes sense. They are revolving around a planet in the circular orbit. So one satellite is taking 1 hour to complete one orbit. Second satellite is taking 8 hours to complete one orbit. Right. The ratio of angular velocity satellite S1 to the angular velocity of satellite S2 is. Now we have that point, right? Angular velocity of one body with respect to angular velocity of other body. All those things are there. So ratio of angular velocity of satellite S1 to the ratio of angular velocity of satellite S2. No, it's not relative. We are just talking about the ratio of two individual velocities. It is not that much, that one. We are talking about the ratio of angular velocities of these two satellites. So clearly it's very simple now, right? It is very simple. Let's say this is the planet. This is the satellite 1, S1. It is moving in this orbit, taking a time of 1 hour. The second satellite is moving in this orbit, right? Second satellite, it is taking the time 8 hours. So clearly you can say that it is taking lesser times, but the distance is also lesser. But you can say that the time period of a certain satellite is 2 pi. The angular displacement is same, 2 pi upon the angular velocity omega 1, right? Let's call it T1. And for the second satellite, 2 pi by omega 2. So 2 pi cancelled out. So it is omega 2 upon omega 1, right? We have to find the ratio of angular velocity of S1 to S2. So we have to find omega 1 upon omega 2. So we can reverse both sides. So omega 2 by omega 1 is T1 by T2. We have to find omega 1 by omega 2, which is going to be T2 by T1. So it is 8:1, right? So 8:1, which is option D. You see that 1:8 and 8:1 is both are there in the options. But 8:1 is the correct option. Why so? Because they are talking about the ratio of angular velocity of S1 to S2. So omega 1 to omega 2 we have to find out. Omega 1 is for this one. Omega 2 is for the second one, right? So 8:1 is the correct answer. Yeah. Now let's move on and talk about the next part, which is the dynamics of rotation motion. So we have clearly discussed a lot of things. Like we have talked about the terms of rotational motion, which is the angular velocity, angular displacement, right, angular acceleration. How are these terms related? We have talked about that without discussing the cause, right, the term that actually creates the change, that is the cause behind the change of angular velocity, which is torque. We have not discussed that. That is something we are going to talk about right now. Dynamics of rotational motion. So now what we are going to discuss, we will talk about the dynamics of rotational motion. So let us discuss that much. Okay, let's go ahead. Now when we discuss about the dynamics of rotational motion, as I have already told you, we are going to talk about the torque, right, and various things about it. Right now the thing is, we can make different kind of numericals about the torque, right, but the good kind of numericals involve vector notations, right. You remember that I can tell you the simple stuff, right. I can just tell you one formula for the torque and I can just move ahead with the another topic, but that is not help you. That is not going to help you if you're going to solve previous year papers, and there are some good problems as well. So what I have done is I have picked one level problems above that as well. Simple problems are there as well, but there are some good problems as well. So the fundamental purpose behind them is to help you with the vector kind of problems, right. So all the problems here are going to help you understand and how to visualize vector dynamics of rotation motion problems in a very clearer way. Let's have a look at like what kind of problems we can expect and the basic theory behind it as well, right. So all the concepts and numerical we will talk about one by one. So what is torque? Torque is basically the same push or pull, but now it is going to have turning effect. So when the force is going to have a turning effect, then that thing is going to be called as moment of force or torque, right. Now you see that the torques will work right like this. So the body, this body, let's say, can rotate about this point, and I'm applying a force at a certain place. Let's say that I'm applying a force over here about which the bodies can rotate. So of course there is no torque, same push but no torque. But the push applied here, it has some turning effect, some torque. Force applied much further away about from the point about which the body can rotate. So yeah, so right now it has maximum torque. So clearly the turning effect of force or torque increases as you move further away from the axis of rotation, right. So this is the door. You try and install the door handle away from the hinge so that it is easier to open and close it, right. And the second thing is also there, the angle. For example, let's say that this is the point about which this thing can rotate, and here you have a long rod, right. Now if I apply this, so about this point, of course this rod can turn up and down. So if I apply a force like this, so I'm pushing it, but the rod does not have any turning effect. There is no turning effect that we can see, right. So I'm pushing the rod like this, clearly there will be no turning effect. So I'm increasing the angle slightly, so you see that some turning effect will be there, right, because this force has one component here and the other component there. So clearly the component which is along the axis like this will have no turning effect, right. The component of this thing which is along this thing has no turning effect. Now if I increase the angle, so yeah, clearly more turning effect we will have. And if the angle is like this, if the force is applied like that, same force but applied like that, right, will have maximum turning effect, yes or no. So same force applied in this fashion will have maximum turning effect. So clearly there are some factors that will decide how much turning effect or torque will be produced by a given force, right. One is how far it is acting from the point of rotation, right, axis of rotation, right. So in the vector format we will not say the distance from the axis of rotation, we will call it the position vector, right. It depends on the position vector. Position vector means if you join this and this, right, so the vector the vector joining the point about which the body is going to rotate, right, to the point where the force is acting, this vector is the position vector right now, right. Okay, so now it depends on the position vector clearly, and also on the amount of force. Clearly if more force is there that is willing to turn the body, clearly more turning effect will be there, but also the angle is there, right. So you see that this force has no turning effect. So if I take the angle theta, right, so clearly you say that the f cos theta, if it is f cos theta is not helping us because it is along it, f sin theta is helping us. So more f sin theta means the more component acting in this way, and that is going to turn it, right? So the component of forces which is along the axis are not helping us in turning the body. So clearly the torque or turning effect of the force, is basically proportional to few things. Torque is proportional to the magnitude of force which is acting, clearly, right? Torque is also proportional to the position vector, right? And the torque is also proportional to sine of theta, f sine theta, whatever that is. So we can see if we join them, and the proportionality constant that will come up in this situation for SI unit is 1. So torque is equals to r f sine theta, right? And what will be the direction of this torque? Because right now I have just written the magnitude. The direction of this torque, if you want to write it in the vector format, it is r cross f, right? So if you extend your fingers in the direction of r and you curl your finger in the direction of force, so you see that this is the direction in which the position vector is there, right? And the force is acting like this, for example. So if you curl in like this, so the direction of torque is like that. So we can say that the torque is also an axial vector. You can also call it pseudo vector. So yeah, this is it. Now this is torque is r cross f. My dear kids, r cross f and f cross r do not have same direction, right? F cross r means you have to put your fingers in the direction of f and turn the direction towards r vector, right? So that will give you the opposite direction. So r cross f is the direction, the notation of that torque, right? Torque is r cross f. I believe that is very, very clear. Let's move on and talk about the more interesting ideas, right? Over here, so yeah, you see that. So this is the plane over here. This plane can rotate about this axis, right? This is the axis of rotation, and the force is acting like that, right? So you can imagine in this way. For example, you can have a plane like this thing, right? Okay, so this thing can rotate about an axis. So I can take an axis like this. So here is the axis, right? You see that this is the axis, very long axis I have, right? So yeah, right now you see that, but it will not rotate automatically. I have to apply a force. So I can apply force in any direction, right? So I can apply the force like this, it will turn, right? I can also apply the force like this, it will turn, right? And I don't have to apply the force on this thing only, right? I can also apply the force like this. You see that? Still it is turning, right? One component of the force is invested somewhere and turning it. One component of the force will be along it. It will not help in turning, but there's one component which is going to turn it, right? So like that. You see that? The force vector is this, right? And the position vector is the vector joining this, the vector joining the axis of rotation, the point about which the body is going to rotate, to the point where the force is acting, right? So if you join them, this is the position vector. Let's say the force is acting over here. So join this point and this point. This is the position vector and this is the force vector. If the force is acting here and trying to rotate it, right? Imagine the turning wheel of that potter, right? So what is happening? So this is the axis of rotation. Join this point and try to call this vector as r vector right now, right? So we will see that in various numerical problems as well, and we will do that in front of us as well, right? So right now the force is acting like this. So if you have to join it, this vector, this is r vector, right? This is r vector, right? And this is f vector. So r vector cross f vector will be the torque produced by this force about this axis, right? So yeah. Now let's look at few things, right? So torque is an axial vector, right? Now we can have multiple forces acting on the body trying to rotate it, right? So you can say that this is the plane, and at different points, at different position vectors, we have multiple forces trying to produce a turning effect. The net torque will be the individual torques of those forces, right? Added in a vectorial fashion. So think about it. If one force is trying to rotate this way, other force is trying to rotate that way, so you have to use negative sign. Net torque will be reduced, right? Okay. For example, a seesaw. A seesaw is something that you can easily understand, right?
You see that one force, let's say one person is sitting here, his weight is trying to push it this way, and another person's weight is trying to push it this way. So you see that this distance is r vector. Let's say this is r vector, and this is the force vector. Let's say the angle is theta, so rf sine theta. So this is the torque produced by this one, and similarly we have the torque produced by this one. So we can say that both the torques are opposing each other. So what will be the net torque? Net torque will be 1 minus the other torque. Torque 1 minus torque 2, right? So minus sign is coming up. That means we have to add them in a vectorial fashion like this. So now this is the very important portion, right? If the point at which the force is acting has a position vector written in this rectangular coordinate xi cap plus yj cap, this is in the vector format, and the force is also written in the vector format ijk, then the torque is r cross f, right? If you have to write down the vector product of two things, how can you do that? You can simply make the determinant, right? So r cross f, torque is r cross f. So in the determinant format, first of all you will write rectangular unit vectors ijk, and then you will write down the coefficients of the first vector. R vector is the first vector, so x, y, z, and then the position vectors of the f vector, which is fx, fy, fz, fx, fy, fz. So this is it, right? So you can simply just move ahead with this one and calculate the requirements, whatever your requirements are. Now, yeah, this is how you do it. And solving a determinant is very, very easy. First you will take this one and then solve this one, and then you take this one with a negative sign and solve the remaining one. So yeah, solving a determinant is very, very easy. This is something I expect you to know, that how to solve a basic determinant, right? 3 cross 3 determinant, right? So this is something you can learn in the basic maths classes, right? All right. So I believe the idea is very, very clear, right? Okay. So yeah, so this is how you solve determinant. Now the next thing is the torque is written like this, right? So let's try to solve some numericals and see few things. So here we have work done by the torque as well. So you know that the work done by force, work done by force is F into displacement, right? So if you want to talk about the force is creating some displacement in the body, so it is going to produce the work done F into ds, right? Or F dot ds, right? So if you integrate it, you will get the total work done in the integral format, right? Similarly, you can write down the work done by the torque in rotating the body, right? So in moving the body, the force is doing the work. In rotating or turning the body, the torque is doing the work. Here you have multiplying the force with the linear displacement, and here you have to multiply torque with the angular displacement. Very easy, right? So from initial displacement to final displacement, integration of tau d theta is the work done, right? Okay. Now let's move on and talk about the next thing, power. So power, we already know that, like in the case of forces, the power is work done per unit time, and you have also represented the instantaneous power as dw by dt, right? dw by dt. So work done by constant force, let's say the force is constant, so work done is F into ds. So the force will come out of this thing, so F into ds by dt, and you call that thing as velocity, right? So F vector dot v vector. So you call that as instantaneous power delivered by the force, right? So now what do you have? You have the torque performing rotational motion, right? So that is also doing some work. This is for the linear terms, right? So right now you can do the same thing, differentiating the work with respect to time, right? Got you this thing. So similarly, now you're going to do the same thing, differentiating the work with respect to time. So here, instead of linear displacement, you will have the angular displacement, and same thing, ds by dt. Instead of that, you will have d theta by dt, and instead of force, now you will have torque. Same things, right? So now you see that ds by d theta by dt is rate of change of angular displacement. Here you have rate of change of linear displacement, it is linear velocity. So rate of change of angular displacement is angular velocity, right? So power delivered, instantaneous power in case of torque is torque into angular velocity. So this is it, right? So yeah, again a very, very important relation that you have, right? Now look at one problem and try to solve it at peace, right? So we will solve it without any issue. Here we have it. What is the torque of a force acting at a point about the origin, right? So what is the torque of this force? Force is how much? 2I minus 3j plus 4k, right? It is acting at this point. So the position vector of this point is 3I plus 2j plus 3k, right? About the origin we have to calculate. So position vector of that point at which the force is acting is already written, right? So clearly right now this is the easiest problem you can have. Torque is R cross F, right? So you will write the first vector into second vector, right? So write down R vector is this 3I. Remember that you don't have to put this vector in the first place. It is not, you cannot exchange it like that, right? So 3I plus 2j plus 3k, this is the R vector, and now you have to take the cross product with the other things. So 2I cap minus 3j cap plus 4k cap. Now what you need to do is, the value of this thing is going to be determinant I, j, k, then coefficients 3, 2, 3, 3, 2, 3, and then the coefficient 2 minus 3, 4, 2 minus 3, 4. Now you just need to solve the determinant and get the value. So it's a very simple 3 cross 3 determinant, and you should be able to solve these kind of simple determinant on your own. So upon solving it, you will have the answer, right? So upon solving it, right, so you solve this part. So 2 into 4, 8, 3 into 3, minus 9, and minus, when you go from down to up, a minus sign comes up, so minus becomes plus, right? Then you go with the second part, and the remaining portions are this and this, right? You do this thing, right? You have done it in the basic maths classes, I believe, right? So 3 into 4, 12, right? And 2 into 3 with a minus sign, so minus 6, right? And when the middle terms comes up, so there is a minus sign that is there, right? And then there is a k. So for k, we have to talk about this little thing. So we have this thing 3 into 3, 3 into minus 3, which is minus 9, and 2 into 2 with a negative sign, so minus 4, right? So just add it up and you will have this vector. So this is the net torque that is also coming up in the vector format, right? So this is the idea behind it. Now let's move on and talk about the next idea. Slightly better problem, right? So we have a triangular plate which is shown in the figure, right? What is happening in this thing? We have a triangular plate. F is 4I minus 3j. It is a triangle plate is there, and a force is applied at a point P. So we have a triangular plate and a force is applied at a point P like this. Okay. All right. So the torque of the force with respect to point O and Q. So first of all, we want to calculate the torque of this force about this point and torque of this force about this point, right? So let us calculate it. So now understand that wherever you want to calculate the torque, right? First of all, think about it. When you are going to calculate the torque about point O, what do you need? You need two things. For when you're calculating torque, torque is R cross F, right? When you're calculating torque, torque is R cross F, right? So whenever you are calculating torque, you talk about two things: the position vector of a point where the force is acting, right? And the F vector, right? So where is the position vector of the point? We can say that when we are calculating about O, so the line joining O and P, this is the position vector, right, of the point where the force is acting, and this is the force vector, right? So first of all, tell me what will be this R vector, right? My dear kids, this is 10 centimeter at an angle 60. So R vector will be this component and this component. So it is 10 cos 60 I cap, 10 sin 60 j cap. So position vector is clearly 10 cos 60, right? Position vector about when we are calculating about point O, right? So you can call it OP vector as well. So this is the position vector, which is OP vector, which is 10 cos 60 I cap, 10 cos 60 I cap plus 10 sin 60 j cap. All right. So this is the vector, right? For example, if you have a vector, right, of 5 units like this, right? So at an angle 60 degree, how will you write this thing in a vector format? So you can see that it has a x component, it has a y component. So it is 5 cos 60 I cap plus 5 sin 60 j cap. All right. So this is how you write it in a vector format like this. So this is how you can write it in this way. So here we have it. 10 cos 60 I cap. So cos 60 you can say 1 by 2. So cos into 1 by 10 into 1 by 2 is 5. So it is 5 I cap plus cos sin 60 is root 3 by 2. So 10 into root 3 by 2 is 5 root 3. So 5 root 3 j cap, right? So this is the position vector that we are discussing about, right? Or the OP vector we can say, okay? All right, so this is the thing. We know the R vector and the F vector is given in the question itself. So the torque in this situation is going to be, R vector cross F vector, right? So in this numerical, you learned about this point, how to calculate the position vector, how to write this vector in the format of I and J, which is vector notation of this thing, right? In the basic maths classes, this is also covered, by the way. So 5i plus 5 root 3 j cap, 5i cap plus 5 root 3 j cap cross force vector. So force vector is 4i minus 3j. 4i minus 3j. All right. So you see that, just solve the basic determinant now. I and j. All right. K is not there. So 5 and 5 root 3 and 4 and minus 3. So solve this thing and you will have your answer in this situation. So I believe the idea is very, very clear, right? And there should be no problem in this one, right? So I hope the idea is very, very clear. Now let's move on and talk about the next part, which is the torque about the other point. So we need to focus now this time when we are going to calculate the torque about the other point, this point. You see that? What do you need? You want to calculate the torque about this point, the force is acting over here, right? So the position vector is the vector joining the point of application with the axis of rotation, right? So you know, so we can join this vector with this point, right? So this is the position vector right now, right? We have to multiply force with this vector, right? So how to calculate this vector? We don't have a direct way of knowing this vector, so we can say that if I know this vector and if I know this vector, so it's a resultant of subtraction of these two. Yes or no? It's a displacement vector, we can say. So it is R2 minus R1, we can say, right? So from here to here we are going, so R2 minus R1, it is the position vector. So we can clearly write it like this, right? So R2 vector, from here R1 to R2 we are going, so R2 minus R1 is going to be this thing. So we need to know here, again, torque is R cross F. No problem with that, right? So what is R vector over here? So R vector is this QP vector, right? QP vector, right? Okay, so QP vector will be this vector minus this vector, right? So OP vector minus OQ vector. OP vector minus OQ vector. Yes or no? I believe the idea is very, very clear, right? OP vector minus OQ vector. So what is OP vector? We have already calculated the OP vector is this, right? This vector we have already calculated, 5i plus 5 root 3. So we can put it 5i plus 5 root 3 j. And OQ vector, this is 10 centimeter along x-axis. So it is 10i. All right. So 5i and 10i are subtracted, it is minus 5i and it is 5 root 3 j. All right. So I hope the idea is very, very clear. Minus 5i and 5 root 3 j. Okay. So I hope the idea is very, very clear. So we know the position vector right now. These are the two things we were required. So the force is acting at this point, right? And the position vector is this vector joining when we are calculating about the point Q. So when we join the Q and point of application, this is the position vector we are interested in. QP vector, we have already an idea about that much as well. So we can just join them. So torque is simply this vector and force vector. So this vector is 5i plus 5 root 3 j and cross product with the force vector, which is 4i minus 3j. So clearly now again we are going to make a simple determinant of 2 cross 2. So it is 2 cos 3. So minus 5 and 5 root 3, right? And then 4 and 3. So you can simply solve it now, right? So I hope the idea is very, very clear. So 3 cross 2 determinant and we can easily solve it, right? I hope there is no confusion in this little part, right? And now we can solve it. So you see that, just look at the first one and second one and solve it, right? Okay. Now let's talk about the next idea, right? Look at this thing. A force is applied on an intersection point of x equals to 2 plane and x axis. Okay. This force is acting on this place. The magnitude of torque of this force about a point 234 is the rounding off to the nearest integer. This is something we have to find out. Then we can solve it like this, right? So options are not given, but we can solve it without any problem. So let's understand that for the calculation of torque, you need two things, right? What is one thing? The position vector at which the force is acting, and the force vector itself. These are the two things you need, right? And once you know these two things, every other thing can be calculated very easily, right? So let us try to visualize the problem first, right? This is the one axis, this is another axis, right? So first of all, this force vector is given. This force vector is acting at a certain place. Where is that place? It is applied on intersection point of x equals to 2 plane and x axis. So x, let's call it, this is x, this is y. So x equals to 2, x equals to 2 plane and x axis. This is the force, this is where the force is acting, right? Randomly, let us say if the force is acting like this, because there are I, j, k, all the components, so the force is also having k component, but I can't make that k component, so this is how I've written it. Okay, so this is the force vector I have, okay, which is acting at this point x equals to 2 like this. Okay, and now we want to calculate the torque, not about the origin. If we had to calculate about the origin, so then r vector was simple, this vector, join this one and this one, right, which is 2i cap. But we don't have to calculate the torque about the origin, right? If we had to calculate the torque about the origin, it will be 2i cap into whatever force vector is given, right? No problem with that. But we have to calculate the torque of this force about this point 2, 3 and 4, right? About this point 2, 3 and 4. So that point is going to be somewhere. So there is going to be z axis as well. And let's say that the point is over here, 2, 3 and 4. Let's call that point as point P. All right. So we have to calculate the torque of this force about this point. So what do you need? You need r vector and f vector. In the vector format, you have to take the cross product of these two things, right? So how to know the r vector right now? So you see that r vector is basically the vector joining the point about which the body is going to rotate to the point of application. This vector is the r vector. We want to calculate the torque of this force about this point. So just join this point to the point of application. This is the r vector we are interested in, right? I hope the idea is very, very clear. And there is no direct way of knowing this r vector, but we can say that it's a resultant of two vectors, right? So it is 2, 3, 4. So if you join it from the origin, right? So this vector is 2i plus 3j plus 4k. This vector is, let's call it r1 vector, right? And this vector is r2 vector, right? So what is r vector right now? R vector is going to be r1 minus r2, na? R vector is going to be r2 minus r1, sorry. Right, this is the idea behind it. I believe the idea is very, very clear. So you see that this vector, this is a force is acting at x equals to 2. So r2 vector, this one, it is 2i cap, right? No problem with that, 2i cap. And r1 vector joined from the origin to this point, it is 2i 3j 4k, 2i 3j 4k. Minus sign I have taken inside. So yeah. So 2i and 2i will cancel out. It will become minus 3i or minus 3j minus 4k. All right. I hope this is the very clear idea about it, right? So this is the r vector, right? Once you know the r vector, this vector is given, calculated. We have calculated this vector, the vector joining the point of application and this thing, right? About the point about which this thing, we have to calculate the torque. So we have to just join it. This is the r vector. We have calculated the r vector, right? So once you know the r vector and the force vector, everything is easy now. Torque is going to be r vector cross f vector, right? So r vector is the position vector of a point where the force is acting. So which is 3j minus 4k. So 0i I component is not there. So minus 3j minus 4k. And you multiply it with the force vector, which is 4i, 3j and 4k. 4i, 3j and 4k. So now what you need to do is take I, j and k, take 0, minus 3 and minus 4, and take 4, 3 and 4. Now you solve 3 cross 3 determinant very easily, right? And you know how to solve these determinants, right? So I believe solving this is going to be piece of cake now, right? So this is the minimum, bare minimum. Solving the determinants of this order should be a bare minimum that you should be able to do by yourself by now, right? And I hope there is no problem in that one, right? So 0 jk, 0 minus 3 minus 4, 4 3 4, and you just solve it. So just for this one, when you solve it, right, so you know that first you will do this, right, then you will solve this one, right, cofactor of the first thing, right? So you see that I this minus this, so you have done that. Then you will do the second part with the minus sign, minus j, and this minus this. So then you will do the third part with the plus sign, k, this minus this. So yeah, you know that, right? So yeah, so torque comes out to be this much. They are asking about the magnitude of torque. So magnitude of torque will be under root x square plus y square. So yeah, this is it. So basic vectors are needed when you are dealing with the vector quantities like torque, right? Okay. So now the question is saying, if the force is 3i plus 4j minus 2k, it acts on a particle having the position vector, this thing, then what will be the torque about the origin? Listen it carefully, right? They are not interested in calculating the simple stuff, right? Here you see force is acting this much, right? So the force is 3i plus 4j minus 2k, right? Okay. It acts on a particle having a position vector, this thing, okay? It acts on a particle having the position vector 2i plus j plus 2k, 2i plus j plus 2k, right? So yeah. Then what will be the torque about the origin? So it is very simple. This numerical has nothing serious in it. So you already know torque, a force vector and r vector. So all you need to do is simply multiply them, right? 2i, j and 2k are the position vector of the point, and force vector are 3i, 4j and 2k, right? So torques, you can simply take r cross f, right? So I thought we need to talk about the origin and all, so but it's very simple then in that case, right? So here it is. So simply just take the determinant, right? I, j, k, 2, 1, 2 and 3, 4 minus 2. This is going to be a simple determinant, and I believe you can solve it. So if I want, I can write it as well. 3i plus 4j. So sometimes they ask you a simple notation kind of thing. So kids who are afraid of looking at vector signs and all, simple vector calculus is not there. So they might lose 4 marks out of this question. But you see that these kind of questions are also there and very simple, right? So you have I, j and k, 2, 1, 2 and 3, 4 minus 2. Simple. How simple is it, right? Now you just have to solve this simple 3 cross 3 determinant, which is very easy to solve, right? So I solve this one, 1 into minus 2 and then 4 into minus 2 like that, and then take this thing and solve 2 into minus 2 and then minus sign with this thing, and then take again with a positive sign 2 into 4 and minus this thing, right? So I believe that is very, very clear. Now let us discuss the concept of rotational kinetic energy, right, my dear kids? We already know in the case of translatory motion, what really happens is a body having mass m is moving with velocity v. So you call the kinetic energy of the body is half m v square, right? But right now a new quantity comes up, right? Why so? In the cases of translatory motion, when we were discussing about the inertia of the body, we said mass is a measure of inertia. And to write it down, when the translatory motion is going on, we can write down the mass over here, right? This is basically telling you the inertial effect, right? But my dear kids, when the things are about to rotate, right, when the things are under rotational situations like this, then everything is changes. For example, This body has certain mass, right? And irrespective of the axis that you choose, it has a certain inertia. For example, if I rotate the body about this axis, right? Or if I rotate the same body about this axis which is passing through the center like this, right? If I rotate it about this axis, the inertia doesn't care about any of that. But one quantity that is now going to be considered as moment of inertia, right? What is that difference? I will tell you. Inertia of a body tells you how hard it is to start or stop a body for a given force, right? So if I say that it's a smaller circle and lighter circle as well, and if I just want to push it, right, I don't want to rotate it, I just want to push it from one place to other place. So both of them are under translatory motion. This one will require lesser force to move and this one will require more force to move because it is having more mass, right? So I said when we talk about inertia, more mass means more inertia, right? And if I take this body, if I rotate it about this axis, if I rotate about this axis in this way, if I rotate about the center like this, inertia does not care about the axis about which this motion is happening, right? Because inertia is not associated with the rotational motion, we can say. We talk about inertia in the translatory motion. But when we talk about the torque, you see that the inertia, the term of inertia is basically telling you the tendency to resist the change in the state of motion, right? My dear kids, that tendency in the case of translatory motion remains only dependent on the mass of the body, right? So this body in the translatory motion is going to resist the change in the how much resistance a body is going to offer. That depends on the mass of the body only when the motion is translatory motion. But when it comes to rotational motion, everything changes. You see that when the axis is this, right? So if I talk about now a new term, moment of inertia, in the rotational term I will talk about moment of inertia. So this quantity is telling me one thing. It will tell me the tendency of a body to resist the change in its rotational motion, rotational state of motion, right? So you see that I apply a certain torque to rotate it right now about this axis, about the axis which is passing through the diameter, right? And you see that for a certain torque, it rotates, it completes some cycles and it stops, right? But when I apply the similar kind of torque and I change the axis right now, remember that the body is same, the mass is same. I have just changed the axis about which the rotation is going to happen. Now you see that the same torque can bring different values of rotation, number of rotations. You see that? Now if I apply the torque, the body continues to rotate very, very easily, right? You see that this body offers one kind of resistance about this axis, right? And this body offers another resistance about the axis perpendicular to its surface, right? So we can say that when we talk about moment of inertia, when the bodies are rotating, mass is not a clear measure of the resistance offered to the change in the state of motion. It is a newer term which is the moment of inertia, right? So in the case of rotational motion, instead of mass of the body, a new quantity will come up which is called as moment of inertia of the body, right? Okay. And moment of inertia about different axes we can calculate. So here we are going to talk about moment of inertia about the centroidal axis and then v square. So instead of linear velocity, the body is rotating. So we will use angular velocity and the half is constant. So half is half. This is the kinetic energy of a rotating body, right? So my dear kids, I believe the idea is very, very clear, right? What is the difference in the inertial components in these two things, right? Half I omega square is the rotational kinetic energy, right? So for a particle, now you look at another term called as angular momentum. So when you had the linear momentum, try to understand in a comparative way. So when you were talking about the linear momentum, so linear momentum was mass into velocity, right? You said that linear momentum was mass into velocity, right? You are just multiplying the magnitude of linear momentum is mass into velocity. Direction is same as this much, right? So I should not be writing in a cross product manner, otherwise some kids might get confused, right? It is just a mass is a constant, right? So it is just like that It is multiplied to the velocity, a number multiplied with the velocity vector, right? So this is the momentum. Right? This is how you write it. Okay, this is the linear momentum of a body, right? Okay, when we talk about the angular momentum, the things changes, right? So what is happening, the angular momentum? How do you define the angular momentum of a body? When you say that, the angular momentum is the similar thing, but in the case of rotation, right? So right now, instead of mass, you will have the inertia, right? And instead of this thing, linear velocity, you have the angular velocity. So linear momentum, angular momentum is I into omega, right? Angular momentum is I into omega. I believe the idea is very, very clear. So linear momentum is mass into velocity. Angular momentum is I into omega. My dear kids, there is a relation between the angular terms and the linear terms. Some of those relations we have already discussed earlier, but this relation we can talk about right now. Angular momentum is equals to R, where the force is acting, the torque is calculated, right, about a certain point. So the position vector of a point where the force is acting, which is turning the thing, right? So R cross P, right? So angular momentum is R into linear momentum. Angular momentum is R into linear momentum. Very simple relation, right? So you can write it in this way: momentum is M into V, right? So M can be taken outside, so it will be R vector cross V vector. So you see that? Okay, R vector cross V vector. So this is how you can write it. This is the relation that you should remember. Angular momentum is R vector cross P vector, right? Now you see. Okay, angular momentum is R vector cross P vector. Now let us move on and talk about the next idea. Okay. So right now you see that if there are multiple forces acting on the body trying to rotate it, so multiple turning effects are there, multiple torques are there. So angular momentum of each one of them can be added up, right? And the net turning effect can be added up like this. So angular momentum is going to be I omega. I have already told you that part, right? So if you differentiate both sides, so dl by dt, rate of change of angular momentum is I d omega by dt. So it is I into alpha. Now you know that torque equals to I into alpha. Initially we have already discussed that. So force is mass into acceleration. And you know that instead of mass, now you will have moment of inertia. Instead of acceleration, now linear acceleration, you have angular acceleration. So now the force is the torque. So same, the Newton's second law in the rotational motion becomes this way. Torque is I into alpha, right? So you see that rate of change of angular momentum giving you I into alpha, which is the torque acting on the body, right? So the net torque acting on the body is equals to rate of change of angular momentum. Reminds us something. Net force acting on the body was rate of change of linear momentum. Net torque acting on the body is rate of change of angular momentum. Wow, there is a relation, right? Again, you see that net force acting on the body is rate of change of linear momentum dp by dt, and net torque acting on the body is rate of change of angular momentum of dl by dt. All right, I believe the idea is very, very clear, right? So yeah, now one more thing we can discuss from this particular point itself, right? What is that point? If there is no net torque, let me try to add the comparative thing, right? So we say that the rate of change of dp by dt is the force, magnitude of force, right? And if the external force, if the net external force acting on the body is 0, the momentum, the rate of change of momentum is going to be 0, or we can say the momentum of the body will remain constant, or we can say that momentum will remain conserved. We interpreted this line as if there is no net force acting on the system, then the momentum of the system will remain constant, right? We applied the idea in the problems of collision and all, right? Now what we are going to do is we will jump on and talk about the same things in the case of rotation, right? We know that the torque is rate of change of angular momentum, right? And right now we can say that if there is no net torque, the net torque is rate of change of angular momentum. If there is no net torque acting on the system or the rotating system, right, there is no net torque, then that means dl by dt is 0, there is no change in the angular momentum, or we can say angular momentum will be constant, right? So we can say Momentum is constant when the net external force is 0. Angular momentum is constant when the net external torque is 0. I believe the idea is very, very clear. Right, this is the conservation of linear momentum when the external force is 0, net external force is 0, and this is the law of conservation of angular momentum when the net external torque is 0, right? So, angular momentum, you have just seen it, I into omega. So, we can say I1 omega 1 is same as I2 omega 2 and all, right? Alright, so when you have a look at this particular problem, so you will find that here it is very clearly written, two particles having mass m each are now attached at diametrically opposite points. The angular speed of the ring will become. So you see that when we are using this kind of terminology, what do we want to say basically, that we have not applied any torque while adding those masses, right? You see that we have just attached two particles when the whole thing was rotating. Read it again. A thin circular ring of mass m and radius r is rotating about its axis. So this whole thing is rotating about its axis. We have a thin circular ring that is rotating about the axis, right? And once it is under rotational process, what is really happening? Two particles, the ring is rotating, and then we attach two particles of mass small m to it, and at diametrically opposite points, the angular speed of the ring will become. So what is happening? So you have initially the ring which is rotating about this axis like this, right? Now with some angular speed it is moving, right? So two particles, after some time what you do, this whole thing is rotating about this thing, let's say with angular velocity omega, right? Now what is happening? The ring is same, right? You don't apply any more torque on it, you just add two little masses on it, right? So now the new angular speed definitely will be different in the previous one because it is much heavier, right? So clearly we can say that we have just attached the masses, we have not applied any torque, in the net external torque is 0, and if the net external torque is 0, the momentum, the angular momentum of this thing will not change. So we can say that the angular momentum of this thing will remain constant. Angular momentum of this thing is I into omega. So I1 into omega 1 will remain same as I2 into omega 2. So just write it down. I1 into omega 1 is same as I2 into omega 2. So this is the conclusion, right? So once you start drawing the conclusions by looking at the question, you start solving the problem for real, right? So I hope the idea is very, very clear. So I1 omega 1 is equals to I2 omega 2, right? My dear kids, what is the moment of inertia I1 for this particular geometry? We can say that moment of inertia will be mr square. Moment of inertia of a ring about this, the axis passing through the center is mr square, right? And in this situation, the total mass on the boundary is m plus 2 small m. So just add them up. So here you have I1 is m, radius of this thing is, let's say, r, mr square omega 1, that is same as m plus 2m r square omega 2. So this r is can be cancelled out, right? So omega 2 is going to be, initial velocity was omega, so we can write omega instead of omega 1. So omega 2 will be, clearly we can say, m upon m plus 2m into omega 1, m upon m plus 2m into omega 1, which is omega only. So I hope the idea is very, very clear, right? So m upon m plus 2m into omega, which is this answer, right? So yeah, so option B should be the correct option, right? So let's move on and talk about the next idea. Very simple problem. Now look at this thing, a thin circular ring of mass m and radius r is rotating with a constant angular velocity of 2 radians per second in a horizontal plane about an axis vertical to its plane and passing through the center of the ring. Okay, all right. This is a problem we have just done. All right. Now you look at this thing, the concept of moment of inertia, right? The moment of inertia. So what is moment of inertia? Now we have some idea about it. Now we can dive much deeper into it. So as I have explained during the numerical as well, moment of inertia versus inertia. So inertia is simply telling you that how hard it is to move the body, or if it is moving, how hard it is to stop it. Basically how hard it is to change the state of motion of a body when it is trying to move on a path, translatory motion, we can say, right? So the same thing the same thing performed by the inertia in the translatory motion, we have the same duties are performed by the moment of inertia in the rotatory motion, right? So moment of inertia will tell you that how hard it is to, change the angular velocity of the body, basically, right? We can, we should be very comfortable with that part as well, right? So now you see that moment of inertia, right? Now you see that what is really happening. This girl, when she is expanding her arm, her angular velocity was lesser, and by the conservation of angular momentum, when she keeps her hands closer, so masses are now closer to her body, right, or the axis of rotation. So that reduces the inertia and increases the angular speed. So this is how it happens, right? So you can say that if you want to write out, we can say the conclusively we can write it in this way, right? Whatever duty is performed by inertia in the translatory motion, so we can say that higher inertia means it is harder to change the linear variables, that is linear velocity and all, right? It is harder to change the magnitude of linear velocity and direction of linear velocity, or you can say simply the velocity vector, right? And higher moment of inertia, if moment of inertia is higher, that means it is harder to change the angular velocity. I believe the idea is very, very clear, right? So you see that there are various factors upon which the moment of inertia depends. For the same shape and mass, we can have different moment of inertia, depending upon about which axis we are calculating it, right? So you see that moment of inertia depends on axis of rotation, definitely. Shape of the body, same mass, if it is given a different shape, you give mass m a shape of a ring, it has one inertia. Same mass is made like a cylinder, it has another inertia. Same mass is crushed and make a solid sphere, it has one inertia. Same mass is made out of a hollow sphere, another inertia, right? So axis of rotation, shape of the body, size of the body, right? How far the mass is located from the center, right? So yeah, and then the last thing is distribution of mass, how the mass is distributed. So yeah, basically these three things are just telling you that same thing, distribution of mass. The first thing is about the axis of rotation, and then you have the distribution of mass, right? So if all 4 points are combined, you can just tell this part, right? Basically by changing the shape, you are changing how the mass is distributed about the axis of rotation, right? By making it a ring, right, mass is distributed in one way, and by making it a sphere, the mass is distributed in another way, right? So this is how the inertia changes, right? Okay, moment of inertia changes, okay? Moment of inertia is always defined with respect to some axis of rotation, as I have already told you, right? So here you have mass m, a single particle at a distance r away from the axis of rotation. So moment of inertia of a single mass about this axis is mr square. So if you have multiple particles, then you have m1r1 square plus m2r2 square plus and so on. So here you see that the moment of inertia of a body does not depend on, so it is mr square. So it depends on the mass of the body, it depends on the mass of the body, right? The angular velocity of the body, it does not depend on the angular velocity of the body, because it is simply mr square. So mr square, not omega. So this should be the answer. And the axis of rotation of the body, by changing the axis of rotation of the body, you can definitely change the r, and that's how you can change it. The distribution of mass across the body, that was the whole point. By changing the distribution across the center of mass, you can definitely change the value of r, and hence you can change the moment of inertia of the body as well. So option B is the right option, right? Okay. Now you look at that moment of inertia for distributed mass system. So you have multiple particles m1, m2, m3 and so on, and they are at certain distances r1, r2, r3. So the net moment of inertia will be moment of inertia of every single particle, just add it up like a number, right? m1 r1 square plus m2 r2 square and so on. Now there are many situations when you don't have separate particles, instead you have a uniform lamina. For example, you can have a disc like this, right? And you want to calculate the moment of inertia of this disc about a certain axis. For example, the axis passing through the diameter, or the axis passing through this center and perpendicular to the plane. There are various options about which the moment of inertia can be calculated, right? Okay. So how to do that? The general idea is just take a small element on the body, right? Take the moment of inertia of that little portion. It is, let's say the mass of this little portion is dm, and it is at a distance r, so dm into r square, right? Sorry, or dm into r square. And now for that little element it is this, and for the entire lamina, if you want, you can integrate it and get the total moment of inertia about the axis AB, right? Okay, so now this is it. Now let's move on and talk about it. So here we can, by the same approach, we can integrate and calculate the moment of inertia of continuous distribution of masses. For example, we have a straight bar, right, like this, and you want to calculate the moment of inertia about this axis. So here you have it. Moment of inertia is going to be you can calculate by that. It is ml square by 12. So if you have a rod of length L, the moment of inertia about the axis passing through the centroid is ml square by 12, right? And it should be, the axis is perpendicular to the axis passing through the center, right? All right. So now you can, in the similar fashion, you can have different geometries, right? The moment of inertia can be calculated for each one of them, right? So you see that the circular ring, for the circular ring it is mr square. It is not necessary that for the circular ring you should have complete circular ring. You can also have a semicircle, or for that matter a arc as well. So about the same center, let's say the center is same as the center of the center of curvature. So basically what is happening, the entire mass, all the parts, imagine that this is made up of different particles. Every particle is located at the same distance, right? R, 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 R. So the moment of inertia about this point is going to be, for this particle, m r1 square, which is r, m2 r2 square, m3 r3 square, m4 r4 square. For all of them, r square is same, that will come out as common. So r square, m1 plus m2 plus m3 plus and so on, m1 plus m2 plus m3 plus m4, which is the mass of this total thing, which is only m, right? So you see that it is also mr square. So if you have a full circular ring, the moment of inertia about the axis passing through the center and perpendicular to the ring. So this, if this is the ring, this is the axis we are talking about, right? So moment of inertia of the ring for the center, about the axis passing through the center and perpendicular to the plane of ring is mr square, right? Circular disc of mass m and radius r, for this one is going to be mr square by 2, right? For the sphere, solid sphere, it is 2 by 5 mr square. For hollow sphere, is 2 by 3 mr square. So these are the basic things you need to remember, right? For different geometries. For standard values, you can remember the moment of inertia of standard geometries. For the disk as well, mr square by 4, right? And now after that, as I said, by changing the axis of rotation, the moment of inertia will be different, right? Will be, the value of moment of inertia will be different, right? So how can you calculate it, right? So there are two theorems that can help us to figure out the moment of inertia of a body. In case you know the moment of inertia of a body about some axis, you can calculate the moment of inertia about the different unknown axis, right? If you follow these two rules, the first rule is parallel axis theorem, right? What that tells us, that if you know the moment of inertia of this body about this axis, right? Let's call this is the moment of, this is the body, and about this axis we know the moment of inertia of this body about this axis, let us say, is I, right? About this axis xy, the moment of inertia is I. Now you want to calculate the moment of inertia of this thing about this unknown axis, which is at a distance a away from the known axis. So what will be the moment of inertia of this body about this new axis? You can say that it is I plus mass of this body is m and square of distance a square. This is the moment of inertia about the new axis. Let's call it x dash and y dash, right? So this is moment of inertia about x dash y dash, right? So you see that this is how you can figure that out. So if you know the moment of inertia about some axis and you want to calculate the moment of inertia about a new axis which is parallel to the previous one, so all you have to do is just add m mass into square of distance between them to the previous moment of inertia, and you can calculate it, right? This is called parallel axis theorem, right? So the current moment of inertia about the current axis is known, and moment of inertia about the parallel axis you can calculate with the parallel axis theorem, right? Okay. Now we have another theorem called as perpendicular axis theorem. What that tells us is, that if you know the moment of inertia about two mutually perpendicular axes which are in the same plane, so the moment of inertia about the axis perpendicular to it, right, you can call that axis as polar axis, will be summation of these two. For example, if this is the body, x and y are in the same plane of the body, and we know the moment of inertia about x and y, right? So we can calculate the moment of inertia about the z axis which is perpendicular to both of them. For example, you look at this. This is x axis, this is y axis, right? This is x axis, this is one axis, this is another axis. Both of them are in the same plane, perpendicular to each other. You know the moment of inertia of this body about this axis. You know the moment of inertia about this axis, right? Both of them are perpendicular to each other in the same plane, right? You just add them up. So that will give you the moment of inertia about the axis perpendicular to the surface, right? I hope the idea is very, very clear. So moment of inertia about the z axis is summation of moment of inertia about x and y. All right. I hope it is making some sense. Right. Let's move on and talk about this idea. So based on that, moment of inertia of the circular ring about different geometries is going to be this. You can download these notes and you can definitely revise it. Okay. All right. So I have written some things on it. So now let's move on and talk about some numerical problems. There are two rings of same mass. Two rings of same mass. Okay. And they are placed such that their centers are at common point. Their centers are at common point. Okay. Okay. And their planes are perpendicular to each other. Okay, there are two rings of same mass and radius. They are placed such that their centers are at common point and their planes are perpendicular to each other. The moment of inertia of the system about an axis passing through the center and perpendicular to the plane of the one of the ring is. It's not range, it's ring. Ring is okay. So what do we have to calculate basically? So the idea is very, very simple. If we can just visualize what is going on, we can calculate it very, very easily. So how can you do that? Let us have a look at this thing. So basically what is happening, we have two rings of same mass and same radius. They are placed such that their centers are common point and their planes are perpendicular. So if one ring has this plane, one ring has this plane, the other ring has another plane which is perpendicular to it. So other ring has another plane perpendicular to it. They have common center like this. Okay. Right. The moment of inertia of system about an axis passing through the center and perpendicular to the plane of one ring. So you see that moment of inertia of this system you have to calculate, right, about an axis passing through the center and perpendicular to plane of one ring. So this is the plane of one ring, right? Perpendicular to plane of this ring is this, right? So clearly it is the diameter of the other ring. This plane which is perpendicular to the ring number 1, let's call it, this is ring 1 and this is ring 2, right? So the plane, this plane which is perpendicular to plane 1, ring 1, right, is also diametric axis, diameter of the second ring, right? Okay. Now we can calculate the moment of inertia about this axis very, very easily. So let's call this axis as xy, right? Net moment of inertia will be moment of inertia of ring 1 about xy plus moment of inertia of second ring about the same axis. Now you see that for the first ring, this axis is axis perpendicular to the ring, right? For the first ring which is placed like this, right, the it is like this, right? The axis is like this. So it is the moment of inertia about the axis passing through the center perpendicular to the plane. It is mr square. So for the first ring it is mr square, no worries about that. And for the second ring, right, for the second ring which is placed like this, right, so this is the diameter and about the diameter it is half mr square. So just add them up and you will have the answer. It is 3/2 mr square. I believe it is making some sense. So the option C is the correct option, right? Option C has to be the correct option, right? So this is how you can attempt these kind of problems and easily solve them. Now you can look at another problem and try to solve that as well. So look at that. Consider a uniform wire of mass m and length L. So what do we need to calculate? We have to imagine a uniform wire of mass m and length L. You can imagine in this way, right? Mass m and length L, okay, right. Now it is bent into the semicircle. It is bent into a semicircle like this, okay. It is bent into a semicircle like this, okay, right. So its moment of inertia about a line perpendicular to the plane and plane of the wire and passing through the center is. So you see that if this is the line of this is the common, you know, a straight wire of length L and mass m, right? Once you turn it into a semicircle of radius r, let's say, right? Once you turn into the semicircle of radius r, because we don't know the radius r, in the question they are giving you the variables L and m. They don't talk about the radius of this thing, right? So let's say that what would be the radius of this thing? So we can say it is semicircle, so the total circumference is pi r. The total circumference pi r is equals to L, right? So the r is nothing but L by pi. Okay. So we have a semicircle and we want to know the moment of inertia about this axis which is perpendicular to it and passing through the center, right? So about this axis we want to calculate. So it is simply mr square. Moment of inertia is mr square, right? So now you know that moment of inertia of this semicircle is mr square, right? So mass is given m and r square is L square by pi square, right? So ml square by pi square is the answer. So option A has to be the correct option. I believe the idea is very, very clear, right? Option A is the correct option. All right. Now look at this question. What is the moment of inertia of a uniform solid sphere of mass m radius r pivoted about an axis that is tangent to the surface of the sphere, right? So this is the sphere. What kind of a sphere? It is a uniform solid sphere. So 2 by 5 mr square about the center, right? Okay, about the axis passing through the center. And we don't have to talk about the moment of inertia about this axis. We know the moment of inertia about this axis 2 by 5 mr square. But we want to know the moment of inertia about another axis which is parallel to this and tangent to this thing, right? So since it is tangent, this distance has to be the radius r, right? And the moment of inertia about this axis, you know, xy, and moment of inertia about the parallel axis you have to calculate. So you know that here we have a useful theorem which is called parallel axis theorem, that tells us if you know the moment of inertia about a certain axis and you want to shift it and calculate the moment of inertia about an axis parallel to the available axis. So the new moment of inertia about the new axis x dash y dash will be the moment of inertia about the known axis plus mass of this sphere into square of distance between these two axes. That's it. So it is 2 by 5 mr square plus mr square. You can call it 5 by 5 mr square, right? So you see that 2 by 5 and 5 by 5, it is 7 by 5 mr square. I believe that is very, very clear. So option D has to be the correct option, right? Now we look at this thing. The moment of inertia of a solid cylinder of mass m, radius r and length L about its axis. It's a direct formula. It is half mr square, right? All right. Moment of inertia of a circular wire of mass m, radius r about its diameter is. So moment of inertia of a circular wire of mass m and radius r. Mass m and radius r. So clearly it is mr square by 2. Again, a very known formula. Right, so option A is correct. Okay, so you see that these derivations you can definitely do at home, but in the exam hall you must remember these basic formulas, right? Sometimes they ask you directly for these basic formulas as well. So here what is happening? One solid sphere A and another solid sphere B are of same mass and same outer radii. The moment of inertia about their diameters are respectively IA and IB. Moment of inertia of their individual mass, individual things are IA and IB, right? So now what you need to do is you need to talk about their moment of inertia about their diameters are respectively IA and IB, such that what will be the relation between IA and IB? Very easy, right? So you see that we have a solid sphere and we have a hollow sphere, right? We have a solid sphere and we have a hollow sphere. So we have one solid sphere for which the moment of inertia is going to be 2 by 5 mr square, right? Let's call it I1. We have another hollow sphere for solid, let's call it IS, and for hollow, let's call it IH. So for hollow sphere, the moment of inertia about the axis passing through the center is 2 by 3 mr square, right? So if you take the thing like this, so 2 and 2 will cancel out, and this can be removed as well. So it will be 3 by 5, right? So you see that the ratio of is this Is upon IH is 3 by 5. So you see that here in the denominator you have a bigger number. So IH, the moment of inertia of a hollow sphere, is bigger than moment of inertia of the solid sphere. So clearly they are calling it IA and IB. Okay, so you can call it IA and IB, no problem with that. So clearly IB is more than IA, IB is more than IA, so option C is the correct option. Now look at this thing. The moment of inertia of a circular ring of radius r, mass m, about the tangent to its plane, right? So we have a circular ring, okay, tangent to its plane. So this is the tangent to its plane. Let's call that axis x dash y dash. You know the moment of inertia about this axis xy. You know the moment of inertia about this axis, and you want to calculate, this is going to be r only. So the moment of inertia about x dash y dash, which is parallel to the moment of inertia, which is parallel to the axis passing through the diameter, right? So this is moment of inertia about xy plus mr square. Parallel axis theorem is clearly applicable, right? So here you have moment of inertia about this axis is going to be mr square by 2, and we have to add mr square, so it is 3 by 2 mr square. All right, so option C is the correct option. All right, so look at this numerical again and try to solve it as well. We have 4 identical discs, each of mass m and diameter a. So this is something which is going to create some mistake. So this is, you can write out a silly mistake. We can expect a silly mistake in this particular part, right? So 4 identical discs of mass m, and each one of them has diameter a. So when you're going to write the moment of inertia of a disc about the diametric axis, it is ma square by 4, but then a is the radius of the disc, right? Here a is the diameter, right? So remember that. They are arranged in such a small, in a small plane like that. So if the moment of inertia of the system about this axis is about this axis, the moment of inertia of this whole thing is this, then what is the value of x in this situation? Okay, so remembering that here, let's say the radius of each sphere is r, so r is nothing but a by 2. So in at last we will put r is a by 2, so that in our brain this thing does not create a confusion, right? We will, if we call it ma square by 4, it will be wrong. The moment of inertia cannot be ma square by 4, it is mr square by 4, right? A is the diameter, because, right? So you see that there are 4 bodies. Let's call the moment of inertia of this body about this axis is I1, for the second body about this axis is I2, for the third body about this axis the moment of inertia is I3, and for this body the moment of inertia about this axis, let's call it I4, right? So all you need to do is to get the total moment of inertia of the system about OO dash is going to be moment of inertia of the first body about the same axis, for the second body, and for the rest of it. So for the first body, the moment of inertia about this axis is going to be ma square by mr is again this is silly mistake I have done. It is not ma square, it is mr square by 4, right? mr square by 4. Okay, then for the second body about the axis passing through the diameter, mr square by 4. For the third body, the moment of inertia we have to calculate about this axis. We know the moment of inertia about this axis, mr square by 4. So there is a distance r, so moment of inertia we have to shift, right? So for the third one, it is mr square by 4 plus mass of the body m into square of distance between the axis, which is r square, plus for the fourth body, moment of inertia about this axis, you know, it is mr square by 4, and you want to know the moment of inertia of the fourth body about this axis. So again you have to shift it. So mr square by 4 plus mr square. So just add them up, and now you will have the answer. So mr square by 4, mr square by 4 times mr square. So it is 1 mr square only, and then you have 3 more. So 3 mr 2 more. So 3 mr square will be the answer. And now we have to know the final answer in terms of diameter a, right? So instead of r, you can put a by 2. So the total moment of inertia will be 3m. Instead of r, you have a by 2 square. So you have 3 by 4 ma square. So now upon comparing, it is x by 4 ma square, and now you have 3 by 4 ma square. So instead of, in place of x, you have 3. I believe the idea is very, very clear, right? So now look at this question as well. So if a solid sphere of mass 5 kilograms and a disk of mass 4 kilogram have the same radius. So we have a solid sphere, all right, and we have a disk. All right, so here we have a mass 5 kilogram, m1, and here we have a mass 4 kilogram, m2. All right. So now we have the same radius. So r1 is r and r2 is also r. Okay. All right. Then the ratio of moment of inertia of the disk about, okay, then the ratio of moment of inertia of disk about an axis tangent to its plane. So this is the disk and this is the tangent to the disk. We are talking about moment of inertia about this axis only, right? And we are taking the ratio with the sphere about the tangent to the sphere. Okay, so this is the sphere and we are calculating the moment of inertia of the sphere also about its own tangent. So this is the moment of inertia of the sphere. So we want to take the ID upon IS. Okay, moment of inertia of the disk about the tangent to the disk, and moment of inertia of the sphere about the tangent of the sphere. So ID upon IS. Okay, this is what we need to calculate. Very easily we can do so. ID upon IS. So what is ID? Moment of inertia of this thing. So we know that moment of inertia of the disk about the axis passing through the diameter is mr square by 4, right? m2 r square by 4, right? Sorry, yeah, it's a disk, right? And this distance is r, right? So about this particular axis, we have to shift it. So m2 r square by 4 plus mr square. So it is m2 r square by 4 plus mr square. We have to shift it. m2 r square. This is a better way of writing it. Now for this disk, for the sphere, solid sphere, it is going to be about its own axis. We know that it is at 2 by 5 mr square. So mass is m1, radius is same, right? Plus about this axis we know, and we want to shift it for this axis, right? So shifting will require mr to add mr square. So m1 r square you can add, right? So r square can be cancelled out, okay? And in the numerator we have m2 by 4 plus m2, which is 5 by 4 m2, right? And the denominator you have 2 by 5 m1 and m1, which is 7 by 5 m1, right? m2 is, you see, 4 kilograms, m1 is 5 kilograms. So you can just put the values. 5 by 4, m2 is 4 kilograms and m1 is 5 kilograms. 7 by 5 into 5, right? So you see that this is cancelled out. The final ratio comes out to be 5:7, right? So the ratio is x by 7 and we are getting 5:7. So clearly instead of x we have 5. All right. I hope the idea is very, very clear, right? So all you see that in this kind of problems, it's a very lengthy problem. They won't ask you this, but again, just for the sake of discussion, we have solved this one as well. So they will ask you either this or that. But anyways, if they ask you both of them, you know that it's a lengthy problem and it will take 1 to 2 minutes. So you can arrange it wherever you want in your paper solution journey, right? Okay. Now we look at this numerical, right, and read it. Moment of inertia of dice of a mass m, right, and radius r. So it is not dice, it's disk, right, of mass m and radius r about any of its diameter is mr square by 4. The moment of inertia of this disk about an axis normal to the disk and passing through the point on its edge will be x by 2m square. What is the value of x? Okay. So you see that this is the disk, this is the axis passing through the center and perpendicular to the plane, right? We know the moment of inertia about any diameter is mr square by 4. So about this diameter, about the other diameter, the moment of inertia about these diameters is mr square by 4, and we already knew that mr square by 4. Now we can calculate, just add them up, moment of perpendicular axis theorem. right? Moment of inertia about z axis or polar axis is summation of moment of inertia about x and y. So it is mr square by 2, right? So moment of inertia you can calculate about this particular axis for the disk, right? So let's call that axis as x, this axis as y, and the axis perpendicular as z. So moment of inertia about z axis is clearly ix plus iy. So it is simply 2 times mr square by 4. So clearly mr square by 2, all right. And we knew that already by default that the moment of inertia of the circular ring, circular disc about the axis passing through the center and perpendicular to the plane is mr square by 2 for the disc, right? Now we know that already, but we need to calculate the moment of inertia about an axis normal to the disc and passing through the point on the edge. So normal to the, if we want normal to the disc, right, but it is passing through the edge, right, like this. So about this axis we want to calculate the moment of inertia. We already know the moment of inertia about this axis, we can shift it and calculate the moment of inertia about this one. So let's call that axis as x dash and y dash. So moment of inertia about that x dash y dash is moment of inertia about this known axis plus mr square, mass of this thing plus into square of this distance. So this is r only, radius of this thing. So mr square by 2, this is the moment of inertia about its own this axis, right, plus mr square. So it is 3 by 2 mr square. I hope the idea is very clear. So it is 3 by 2 mr square. So instead of x you have 3. Alright, so 3 by 2 mr square, we have solved this one, and now we can move on to the next problem. Alright, so now the next concept is the radius of gyration, right, the radius of gyration. Now the idea behind the radius of gyration was very simple. Since comparing the moment of inertia of individual bodies is very complicated, right, we cannot directly compare the moment of inertia of this body with the other body because it depends on so many things, right. But we want a number, right, we want a number k. This thing is k, radius of gyration is basically that quantity. Radius of gyration is basically that quantity square of which if multiplied with mass will give you the moment of inertia of the body. Okay, so that defines everything, because we see that moment of inertia for different bodies is different. For some it is mr square by 2, for others it is 2 by 5 mr square, for some it is 2 by 3 mr square. So it is very confusing, right? But you see that for radius of gyration everything is same, everything seems to be same, right? So you see it is basically the effective distance from the axis. What is this? Radius of gyration about an axis is the effective distance from the axis where the whole mass can be assumed to be concentrated, right? Basically what is happening, moment of inertia of a single particle about this axis, if it is distance r, it is mr square, right? Moment of inertia of this single particle about this axis is mr square, no problem with that, mr square. Now for a single, now if we had a single particle, then calculating the moment of inertia of single particle is easiest about this axis, right? If you take the particle away, the moment of inertia will change and a new value will arrive, right? So now if we can derive a method, if we can derive a strategy, right, where all the shapes, all the geometries can be concentrated at a point like this point mass, right? If you have a disk or if you have a ring or whatever, you have assumed it to be concentrated at this particular point at a very specific distance, right? And it gives you the same value, mr square, right? The moment of inertia, if you have assumed the ring concentrated over here, and it gives you the same moment of inertia as it would give you while you calculate the moment of inertia by its own formulas. Our job is solved, right? So you see that it is effectively that distance from the axis of rotation at which all the mass, irrespective of the shape, can be assumed to be concentrated, and the whole problem, irrespective of its shape and mass distribution, converts into a single particle problem, right? So yeah, you have this thing. Radius of gyration of a body about an axis is the effective distance from the axis where the whole mass can be assumed to be concentrated. So the moment of inertia remains the same. Yeah. So it is I is mk square. So we have assumed that all the mass is assumed at a distance k, right? Whatever geometry you have, we have crushed it, and that distance k, we have assumed that the mass is concentrated. So the moment of inertia is mk square. I believe the idea is very, very clear, right? So for different geometries, we can calculate the radius of gyration, right? So the radius of gyration for this particular situation, for example, radius of gyration for a disk about an axis perpendicular to the plane and passing through the center of mass, right? So this is the disk, axis perpendicular to the plane and passing through the center of mass. This is it, right? So the radius of gyration about this axis we can calculate, right? It comes out to be radius of gyration is under root I by m. So I, which is the moment of inertia of this thing, about this thing, it is half mr square, right, upon mass. So it comes out to be r by root 2. That means we can consider the entire disk is located, this is the axis of rotation, at a distance r by 2. This is r, this is r by 2, right? Entire disk is just another particle. Let's say the mass of the entire disk was m. So this small m particle is located at distance r by root 2, and if we assume this thing, we can calculate the moment of inertia of this single particle m into this square, and again m into r by root 2 square is mr square by 2, right? So it gives you the same moment of inertia without considering that it was a shape, it was a disk or anything else, right? Again, a very huge benefit. Okay. Alright, so now have a look at this particular numerical and try to solve it. So it's saying that the ratio of squares of radii of gyration of a circular disk and a circular ring of the same radius about the tangential axis is. So we have a circular disk and a circular ring. Alright, so let's try to draw it. We have a circular disk, right, and a circular ring. So this is the disk and here we have a ring. All right. So about which axis? The tangential axis. Okay. So they have the same radius and this is the tangential axis we are talking about. All right. So you know that for the disk, the moment of inertia is about this axis, we know mr square by 4, right? And we can shift it to this place by adding another mr square with that, because this is r, right? And this is a ring, right? So the moment of inertia about this axis is something we can calculate, right? Which is mr square by 4 plus mr square, right? So you can say that it is 5 by 4 mr square, right? So now you can let's call it I1. Similarly, I2 in this situation is going to be here you have a ring. So about the diametric axis, you know that the moment of inertia for the ring is going to be mr square by 2, and you add another mr square to that. So mr square by 2 plus mr square. So this is the moment of inertia about this tangential axis, right? So clearly we can write down that as 3 by 2 mr square. Okay. Now what is happening here? You can write down the moment of inertia I1 as mk square. If you do that, this is mk square, right? And I2 also as mk2 square. So you can write down an mk1 square and mk2 square. All right. So now the mass, both the things have the same mass, right? The ratio of this thing, it has the same radius about this particular thing. So yeah, so the mass and mass and radius is same, right, for both of these things. So clearly, even if it is not same, it is cancelled out on both sides. So you need not to worry about that. So radius are in any way same. So we have to talk about the ratio of a square, right? Ratio of a square of this thing. So k1 square is to k2 square. We have to talk about k1 square upon k2 square. That is nothing but 5 by 4 r square and 3 by 2 r square. So this is cancelled out. So this is going to be 5 by 2 divided by 3 by 1. So you just reverse it, 1 by 3, right? So it is 5 by 6. 5 by 6, that is option B. B is the correct option, right? So very simply we can calculate these kind of problems, right? So what do you need to do, right? You just calculate the moment of inertia just the way you have done so far, and you equate that moment of inertia with mk square to calculate the further parts, right? So let's see that if the radius of gyration of solid sphere is 35, calculate the radius of gyration when the axis is along the tangent, okay? So radius of, if the radius of solid sphere is 35, just the radius is given, not the radius of gyration. So radius is given, it is 35 centimeter. So my dear kids, all the options are also in centimeters, so we don't have to convert it into any other units. So radius of this thing is 35 centimeter. Calculate the radius of gyration when the axis is along the tangent. So you know that about the axis passing through the diameter of this thing. So the moment of inertia of this thing is 2 by 5 mr square, and about this axis we are talking about, which is passing through along the tangent. So about this axis, the moment of inertia will be 2 by 5 mr square, 2 by 5 mr square plus mr square, right? So you have 5 by 5 mr square, so it is 7 by 5 mr square, right? So let's say that the radius of gyration in this situation is k, right? So just put, instead of this thing, you put mk square. So you see that mass is cancelled out, and k will be this thing, 7 under root of this thing, under root 7 by 5 r. All right. So r is given in 35, so you can put the values and calculate it further, right? And just solve it. Okay. So that's it, right? You can solve these kind of problems very, very easily. Just you need to know how to calculate the moment of inertia, and the rest is very, very easy. Okay. All right, so let's look at this particular question and try to solve it as well. So the moment of inertia of a solid sphere about the axis passing through the center of gravity is 2 by 5 mr square. We know that. Then its radius of gyration about the parallel axis at a distance 2r from the first axis is. So radius of gyration about this thing, about this axis, which is at a distance 2r from the first axis. So the first axis is here and 2r. So about this axis, the moment of inertia will be 2 by 5 mr square plus m into this distance square. So m into 2r square, right? This is the moment of inertia, right? So now we have to find out the moment of inertia only. We don't have to find the radius of gyration in this case. Okay. We have to find then its radius of gyration will be. So yeah, we have to find the radius of gyration. So put instead of I, mk square, right? So mass can be cancelled on both sides. So here you have 2 by 5 r square and you have 4 r square. So it is 2 by 5 r square, and 4 r square can be written as 20 by 5 r square, right? So it is k square, right? So 20 and 2 is 22 by 5, r square is k square, right? So k is going to be under root 22 by 5 into r, right? So which is the option B. Okay, I hope that is very, very clear. Now look at this question and try to solve it as well. 4 spheres of diameter 2a and mass m are placed with their centers on the 4 corners of a square of side B. Okay, so 4 spheres of diameter 2a. So we have 4 spheres of diameter 2a. So this is one sphere, this is another sphere, right? And they are placed at the corners of a square of side B, right? So this is one sphere, this is another sphere. So all of these spheres have diameter 2a. So they are placed on the corners of a square, and the length of this square is, the side of this square is B, and you know that the whole thing, the diameter is 2a. So this part is a only, this part is a only. All right. So now we have to talk about the moment of inertia of the system about an axis along the sides of the square. So we can take any side. Let's say that this side, we want to calculate the moment of inertia of this thing about this side, right? A moment of inertia of the whole things about this square. So this is first sphere, second sphere, third sphere, and fourth sphere. So for the first and second sphere, the axis about which we are calculating the moment of inertia is basically the axis passing through their diameter itself. So 2 by 5 mr square is the thing we are discussing, right? So net moment of inertia will be moment of inertia of first and second sphere plus third and fourth sphere, right? So for the first and second sphere, the thing is passing through the diameter itself. So it is 2 by 5 mr square plus 2 by 5 mr square. All right, and what is r here? A plus I3 and I4. So you see that for this one, the moment of inertia is 2 by 5 ma square plus m into b square, right? Because about this axis we have to calculate, and we know the moment of inertia about this axis ma square by 2 by 5 ma square, and we can shift it over here. So for I3 it will be m a square 2 by 5 ma square plus m into b square. And then same goes on for the sphere 4 as well. 2 by 5 mr square plus mb square, because this side is also b, it's a square, right? So you can multiply this thing with 2, right? So just add it up and you will have the net moment of inertia without any problem, right? So yeah, you can do it very easily, right? All right. So you just add it up, 2 by 5 ma square into 2 and this into 2, just add it up and you will have the answer. Now look at this question, try to solve it. The radius of gyration of a cylindrical rod about an axis of rotation perpendicular to its length and passing through the center will be. So you know that for a cylindrical rod it is ml square by 12, right? And we have the moment of inertia for a cylindrical rod passing through the center is going to be ml square by 12. And we want to find the radius of gyration. So radius of gyration, let's call it I is equals to ml square by 12, and just in place of I put mk square is ml square by 12. So m will be cancelled out, so k square is l square by 12, that's it, right? So we want to find the value of k, the given that the length of the rod is 10 root 3, so you just put the value of length and k can be figured out. All right. So yeah, this is it. Just put the value of L, 10 root 3, and you can solve it further. You can put the value 10 root 3 and root 3 can go inside the root. Okay, let's do that in the next step. So it's a 10 root 3 by 12. So it is 1 upon 4 and 10 by 2, which is 5. I believe the idea is very, very clear, right? And there should not be any confusion in this particular part, right? Now look at this numerical as well. So what is written? Solid sphere A, right, is rotating about the axis PQ. If the radius of the sphere is 5 centimeter, then the radius of gyration about the PQ is root x. What is the value of x? Very simple numerical. We can solve it very easily. So here what is happening? First of all, write down the moment of inertia about this axis. So moment of inertia about PQ is going to be moment of inertia about its own axis, which is 2 by 5 mr square plus mass of this body into square of this distance, right? So mass of this body into square of this distance, which is 10 centimeter, right? Because the final answer is in centimeter, so we don't have to convert it into meters. So moment of inertia about this axis, we have to find the radius of gyration. So write down I as mk square. So here we have 2 by 5 mr square, r is 5 centimeter plus m into 10 square. So m is cancelled out on both sides. So square of k is 2 by 5 into 5 into 5. So this is cancelled out and this is 100. So it is clearly square of k is, so k is under root 110. So right now you see that answer is under root x. Here you get under root 110 centimeter. So clearly under the root you have x, which is 110. So answer should be 110. Compare it. It is 110. That is your answer. Now let us talk about the idea of equilibrium of rigid bodies. Equilibrium of rigid bodies. What is the meaning of that, right? Let's understand this particular part. So equilibrium of rigid bodies means there should be no change in the state of motion. When we talk about equilibrium in any sense, means we don't want the state of motion of the body to change. Changing state of motions mean there is an acceleration in this situation, right? Changing state of motion means there is acceleration in that situation, right? So here what is happening, equilibrium of rigid bodies, when we are saying, basically we meant by that, right? Equilibrium of rigid bodies means if there is only translatory motion, all right. So translatory motion will remain under equilibrium when there is no change in the linear momentum. That means the net external forces are 0. That's it. So in that case, linear acceleration will be 0 as well, right? And here you can say that linear momentum is going to be constant, right? This is what we mean by translatory equilibrium. But my dear kids, if the body is free to rotate as well, right? So there is no net force acting on the body. Can the body still change the state of motion? Yes, it can. You see that. Let's say one force is acting 10 Newton this way and the other force is acting at the other point, same 10 Newton the other way. Both the forces are 10 Newton acting in the opposite direction. They will cancel out each other. Net force is 0, right? So for forces, there is equilibrium, but the body can rotate about this point, let us say. So they will also turn the body, and we don't want that. Right now, these two forces are turning the body like this, producing a torque, right? So they will change the rotation, they will, produce the angular acceleration in the body. We don't want that, even that as well, right? So if something is under total equilibrium, if a rigid body is under equilibrium, that means there is translatory equilibrium and along with rotational equilibrium. Rotational equilibrium. So rotational equilibrium means there is no net torque, right? That means there is no angular acceleration, and that means the angular momentum is constant. All right. I hope the idea is very, very clear, right? Let's move on and talk about the next idea. Okay. So translational equilibrium, net force is 0 and all that, all those things, right? So we have already seen that. And for the rotational equilibrium, this thing net torque should be 0, right? So let's look at this particular question and try to solve it. So what is written over here, right? A heavy iron bar of weight 12 kilogram is having its one end on the ground. A heavy iron bar has one end on the ground and the other end on the shoulder of a man. So let's say that these are the axes, and here you have the man standing like this. So this is a very heavy iron bar. One end is on the ground, other end is on the shoulder of a man. So here I have placed it through the head, but you just get the idea. So this angle is 60 degree. The mass of this thing is 12 kilograms. So it is going to act at the middle. Length is not given. Let's call it L by 2. L by 2. This is the middle point. Let's call the total length is L. So here 12 kilogram is acting. 12 into G, 120 Newton is acting. This angle is 60. So it is 120 cos 60 and this is 120 sin 60, right? Now you see that there are going to be normal forces over here and over here, N2 and N1, right? Now because the whole rod is under equilibrium, so there will be no net force and no net torque as well, right? The whole thing is under rotational equilibrium, so there will be no net force and no net torque. So if I try to do the no net torque thing, if I say that the net torque of this thing is going to be 0, so clearly what will happen, about the point O, calculate the net torque. So this N1 will have no net torque about the point O, right? Look at this thing, about this force 120 cos 60 into L by 2, right? So it is 0 for this one. This N1 is acting at the point O itself, so R vector is 0. So it will have no net torque. But for this one, you see that it has two components. One component is acting along the rod itself, so it will not produce any torque. But this component 120 cos 60 and this is L by 2. This will produce a torque. So L by 2 into 120 cos 60 plus, right, the torque produced by this other thing. But now you see that here you have the torque produced by this thing in this direction, and here this particular force N2 is producing a torque in the opposite direction. You call that one as positive, so this one has to be negative, right? Plus minus of N2 into L. So the whole thing adds up to be 0, right? Now what is happening? This 2 and this is cancelled out, it becomes 60. Cos 60 is 1 upon 2. So 60 into 1 upon 2 is 30. So you have 30L minus N2L. So L is cancelled out. So N2 is what? 30 newtons. All right. Now you see that the options are given in kilograms. So he is experiencing 30 newtons. But how many kilograms he might be experiencing? The value of G is, 10. So in kilograms, it is 30 by 10, which is 3 kilograms. He is experiencing 3 kilograms, right? The total weight is 112 kilograms. Out of that, total mass is 12 kilograms. Out of that, on his shoulder, he will experience as if 3 kilogram mass is there, right? All right. Now, there is a comparison chart, right? So here you can see that very easily, right? There is a straight line motion with constant linear acceleration, and then we have rotational with constant angular acceleration. So clearly you can say there's a chart, right? And we have seen this chart, or we have seen all these parameters when we were discussing the kinematics of rotational motion, right? You can go through that very, very easily, right? And all the relation between the terms, again, I have explained all that already. So here we have discussed everything that was required to be discussed in this particular chapter as far as the NEET syllabus goes, right? I believe you have understood each and every concept in the extremely detailed fashion. Now what you need to do is just go ahead on the app and practice the DPP at your end. So that will give you a confidence that you can solve the similar problems if they are asked in the exam, right? So on that note, let's end this class over here only, and I'll see you there in the next class.